Better. Okay, good morning, everyone. Thanks for being here early this morning. My name is Orian Chabinin. I'm postdoc at IREP. I will be your chair for the first half of this morning. So first we can thanks really François and all the organizing team for the dinner yesterday. I think you all enjoyed it. That was really delicious. So thank you again. So back to science, we're going to start this morning with two talks from lessons from ESA orbiters, and we're going to start with Colin Wilson from ESA, who's going to tell us about Earth's contribution to Mars atmosphere from ESA's orbiters. Colin's up to you.
Excellent. Okay, thank you. Thanks for the invitation to give this talk. I'd like to spend half my time telling you about in principle, I wanted to spend my time telling you about the great things we do for Mars climate, constraining it through time. But a lot of that work's been done by others. You've seen a lot of results from our missions already in other talks, so that takes the pressure off me. But in any case, I want to spend half my time talking about our existing orbiters, and then also want to spend half the time talking about what might be next on the agenda and what we're working on. So let's get cracking. So Mars Express, you've seen lots of things, lots of presentations about that. Here's your cheat sheet on the right, in case you don't recognize all the acronyms of our instruments. But we have a suite of 8 instruments, and they look at everything from the subsurface and surface up to the atmosphere and ionosphere. The short answer is it's still doing really well. We are now over 10 times its nominal mission lifetime, and it's still doing well. So it's a great piece of engineering and science, still getting great science data. The current status is we're funded until the end of 2026, and we are now applying for a mission extension to operate in 27 to 29. The spacecraft appears technically in good shape, ready to do that, and we're making a science case that we've got a lot of good science to do. So I thought I'd take this opportunity to walk through some of the points of what we plan to do in the next 3-year extension, so that if you are in a position of judging extensions or talking to those judging extensions, you can also express your enthusiasm about the great science. So just going through in the subsurface, so one of the sort of discoveries, one of the results causing a lot of excitement is from the subsurface sounding radar MARSIS. There are regions in the south polar layer deposits where the reflection from the base of the ice sheets is stronger than the reflection from the surface, despite having to also travel through a kilometer of ice to get there. So the explanation for this is not clear. It does happen to be what you would expect to see if there were liquid water down there, but of course it's very difficult to explain liquid water below, in such a cold region. So it could be, and also we're not talking about lakes of water the way you might have under the Antarctic ice sheets. It could be interstitial liquid water. It could just be locally warm clays and things. But if you have cold clays, cold materials, regolith, it's very difficult to produce the surface reflections, the subsurface reflections we're seeing. So that is that's an area of lots of active debate. Now, in terms of new observations and what role they have, the MARSIS team has completely rewritten their flight software and uploaded onto the spacecraft. So we now have a much more sensitive instrument capable of doing much longer sounding passes at a time. One of the peculiarities of the drifting pericenter is that we haven't actually had a pericenter over the South Pole for many years now. So we're looking forward to having night side pericenters over the South Pole again for the first time in this mission extension. So that means we should get good data again. So this would be an important target in the extension. Surface, so we have already imaged most of the surface. Because of the elliptical orbit, the resolution varies, and they are still trying to fill gaps in the global topography product. But we have a much more sensitive instrument capable of doing much longer sounding passes at a time. One of the peculiarities of the drifting pericenter is that we haven't actually had a pericenter over the South Pole for many years now. So But we're quite close to being able to produce a global topography product at 50-meter spacing over the planet, which would be a great resource. Many publications already use the 200-meter combined MOLA HRSC DEM. So this would then supplant that with an even finer topography product to use as your base maps. And also not just be a topography product, but have co-registered multispectral image data at even higher resolution. So again, this would make a great base map. So we're still just trying to do some remaining gap filling to deliver that product. So also on surface science, the Omega team, I'm not sure if John's already in the room, but they've got lots of new observation campaigns planned. So what you see here is if they focus on the anti-solar direction, then you get peaks in the phase function, which can tell you about surface composition and ices and grain sizes and things, as they're using that. There's also renewed use of this infrared channel, which had been on hiatus for the last few years due to cooling problems, but that's back in use, so doing more characterization. Moving up to the atmosphere, so here, once again, this is a long data set of over 20 years of data, and we'd like to continue that so that we get a longer climatology and chance of seeing more unusual events or usual events and extend that characterization. So that's more of the same, but in terms of what different things, there's been an increased focus recently on using the imagers for dynamical features. It's like these Lee waves here, these gravity waves. This is the Arciamon's elongated cloud feature caused by winds advecting up the side of the volcanoes, and that's seasonal but comes back in repeated periods. So there's things like that we can look at, and HRSC has started doing more limb imagery, so getting these really high altitude clouds, and so we're trying to get more of those. Finally, in the upper atmosphere, ionosphere, and sort of solar wind, we have this 3-year extension would take us to the end of our second, completion of our second solar cycle, solar activity cycle. So we'd like to complete that. There still continue to be new results from MEX, exciting new results, also often in collaboration with other missions like MAVEN. So this is a recent paper here. So in some rare solar wind conditions, the bow shock can completely disappear, which when that transport barrier disappears, then you can both have increased, deeper flux of the solar wind into the atmosphere of Mars, but also escape, even upstream escape from Mars. So we don't know yet what the implications of that would be for long-term evolution. So more study of these extreme solar wind conditions is on the radar, on the menu for MEX and the extension. I mentioned here collaborations. Well, let's crack onto that, because one of the exciting things, particular to this mission extension, we'd like to keep on our existing collaborations with MAVEN and others, but 2 new ones we can look at. Well, I just want to mention Phobos. So all these shape models from Phobos, all the ephemerides from Phobos, largely they're based on observations from Mars Express, because we have all these close flybys of Phobos. And so we want to keep doing that, particularly as the MMX mission approaches. So MMX will be operating at Phobos and Mars from 27 to 29. I was just going to say here, for the MEX observations, we now have, with the Marsis reprogramming, we have a Phobos sounding mode, and we've started using that as we go past Phobos to see if there's any hints of internal layering and things like that. So speaking of MMX collaboration, there's a lot of detail on the slide, but the important thing here is basically it would be at Phobos from 27 to 2030, and we have plans for what to do together. So some of it is Phobos science, some of it's sort of solar wind interaction science, and some of it is looking at the Mars atmosphere. So we get beautiful vertical structure from radio occultation, and if we co-locate that with MMX MIRS observations, then we get a nice collaboration. I just put in this picture of a collaboration meeting because you may recognize the building in the back. We had that here at Jussieu, so MMX collaboration meeting. And then the other really fruitful and promising collaboration will be with the Escapade team. So Escapade launch is coming up soon, very soon, hopefully, so we hope that goes well. They would then be operating at Mars. They have a nominal mission from 28 to 29, so that's ideally timed for our mission extension. And they're really complementary payloads. So Escapade is focused on all the charged particles, but they have instruments we don't have on MEX and vice versa, so that'll be a really great collaboration. Turning now to TGO. TGO is working well. Spacecraft is in excellent condition. It's got plenty of fuel, not only to keep operating as currently, but also it has fuel reserved for orbit change maneuvers in case it needs to do that to support ExoMars rover landing. So it's in robust health, and the flight control team's keeping very good care of it, and the instruments are great. We've heard other things, isotope profiles and so on, so I'll just give you a couple highlights. There are still no methane detections from TGO. I feel I should say that every time. We do keep looking, we do keep measuring. The results are always indistinguishable from zero, so they're very, very close to, we get new upper limits, but there's no detection so far. HCl, on the other hand, is highly variable and has proved a gold mine for understanding atmospheric variability in chemistry and so on. One of the latest things, there's a list here of some of the results coming out from this, even new improvements in modeling this year. One of the things being looked at is there's a lot of, most of the HCl detections are in the dust season, so associated with dust lifted from the surface, but there is a persistent and recurrent detection at this latitude at this season. And so there's work on trying to understand whether that might be a surface source for this HCl, which would be quite exciting. So watch that continuing story. Just on the surface side, so CASIS has a great role to play in collaborative observations of the surface and mapping terrains which might tell us about the past. This is a video put together from CASIS imagery. So just CASIS is really useful for these sort of regional scale or slightly wider than HiRISE, but the multispectral imagery is very well calibrated, and you can do mineralogical mapping and so on with that. So this is this result from Joe McNeil about mounds near the Oxiel landing site, which preserve a whole series of different layers, telling us about the history of water in that area. I should have put another slide in here in terms of recent results, because we looked at Comet 3I Atlas when it was on the far side of the sun, and you'll find that online if you want to see that, but that's another recent highlight from TGO. I wanted to turn now to future Mars missions, because we all like to talk about future Mars missions. So just a reminder, we have two directorates at ESA which are involved. One is the science missions, science directorate, so that does astronomy and so on. That's where MEX is. And then we have the exploration side. And so this is the menu of things to discuss now. So on the science side, you have the M. Matisse mission, which is one of 3 finalists in the next medium class mission. They are approaching their down select. The review process will be happening over the next few months, and then the down select is in June next year, so wish them luck or support, however you can do that. On the exploration side, priority number 1 is to get the ExoMars rover, the Rosalind Franklin rover, to Mars. This is a statement of some of the current activities, so there's still progress. They're still working towards the 2028 launch date. ESA is looking at options, mitigation actions if the NASA support were to be cancelled or reduced compared to what it had originally been. But we are still on track for that. So the next program is Mars Sample Return, and Europe's main contribution to that is the Earth Return Orbiter. I just put these extra pictures in here, not just the sort of computer image, but there is flight hardware being delivered, being built and delivered now. So Most of the flight model deliveries will be completed within the next sort of year or so. So this is a spacecraft which is being built. And so then the question for ESA management is or the member states also, is what do we do with this orbiter? Because progress on the NASA side is relatively slow towards things like the capsule return system. So there's a discussion, there's a study going on about what we can do with that orbiter. The working name for that proposal is Zefiro. The reason it's called Zefiro is partly because ERO is in the title, and the rest of it, Zefiro, is inspired by the god of gentle winds, not the violent winds, but the god of gentle westerly winds, showing that it could carry a payload, including atmospheric science, measuring winds. So ERO is a huge spacecraft and was designed to carry this 600-kilogram return vessel to Mars, so it could carry up several hundred kilograms. So it is a great opportunity, both for remote sensing payloads, but then also could carry small sats, tech demonstrators, things like optical comms. The caveat here is that if we get too greedy and try to put too much on it, then that whole complexity will delay the launch even further. But so this is a study which is going on now. There's some details here about the orbit. What happens next for this depends on discussions coming up at the big council at an ministerial level, which happens next month. So there should be some more clarity on this soon. If we do go ahead with this, then the next step would be a request for information for potential payloads. And the intention would be to put that out in December this year. So that's a relatively, it's not a proposal, it's a relatively brief, two-pager telling us about size, power, mass, things like that. The other thing a lot of you are aware of is LightShip. So the idea with LightShip is this again comes in the queue after, this is a study for future missions, it comes in the queue after rover and MSR. LightShip was intended as a next generation satellite. It's intended as a delivery vehicle and provider of relay and nav services. So each LightShip, because there would be more than one, each LightShip would deliver one or more satellites to Mars and then go into a high sort of near equatorial orbit for relay navigation. And the first passenger would be this thing called Spotlight. So sometimes you hear about LightShip and Spotlight. So just how we defined the science themes for this, we had a science definition team for LightShip. They defined a set of science themes which are largely based around atmospheric dynamics. Remember, this is a high altitude platform, so a bit like geostationary weather satellites. It's great for getting a synoptic full disk view. And so they came up with this list of the science themes. We had a similar thing for Spotlight, which was the low altitude platform. And so they had, again, a similar set of themes, except focused on the surface. The picture in the background is supposed to demonstrate the importance of high-resolution imaging for exploration purposes. There you can see the rover tracks if you look very closely here. Yeah. And so based on those themes, we then had an announcement of opportunity and made a science and technical review. And then based on that science and technical review, the recommended selection of payloads is listed here. So on the high-altitude platform, you have thermal and sort of UV vis imaging, full disk imaging at fairly high spatial resolution, coupled with a sub-millimeter sounder, which would give you winds and volatiles, particularly in the middle atmosphere. And then that's coupled on the lower atmosphere with a Doppler wind lidar, which gives you dust and winds, particularly in the lower atmosphere, as well as then a sort of a follow-on from XRISM imaging IR spectrometer. There were things which were not in the AO because they were assumed to be part of the payload, high-res imagers, radio science, and so on. But anyway, this is the list of recommended payloads for that LightShip study mission. The other study mission on the books is a next-generation lander. So ESA wants to develop precision landing technologies and so on. And so this is the reference payload, which is on this mission. So what next for that? I mean, obviously, as scientists, we want to know what's going to be on the science payload. So the next step for that would probably be to have a science definition team call at some point. When that happens depends on what happens with all the other missions as well. So the summary of those slides is here in this figure. So this figure was also presented in a community briefing, which happened on the 29th of September. This is a sort of one-slide summary of the proposal. This is a proposal of what ESA is putting to the member states at this ministerial council next month. And remember that what happens depends also on how much funding goes into the program. This is an expensive program, so we'll see what comes out. But basically, you can read this in several slices. We have our current orbiters on the left, and then the next slice, very much in the next 5-year period, is to get the ExoMars rover off. And then probably the next priority after that is to do something with this orbiter, which is already being built. And so whether that's ERO or whether that's this Zefiro concept or something else is to be decided at the ministerial. And then in the next slice after that, there's an orbital mission based on Lightship and a lander based on this metal concept. So that is the summary. So I've tried to summarize everything in this slide. So you have, you have these sort of adopted missions, you have the studies going ahead, and of course you've got our current missions today, and a 1 in 3 chance for this mission candidate. So with that, thanks. I welcome questions. I do want to just highlight that there is intended to be another community briefing after the ministerial on 8th of December at 11 a.m. And if you want to make sure you get the link for that, if you sign up for the newsletter at this link, then you will hear about it first.
Thanks very much, Colin. So, question time. Please come to the mic. And yes.
Hi, Colin. Michael, Mission at JPL. Did I see on the previous slide that metal was flying before Lightship? Or
essentially, that is how it's written here. But I would, since there aren't dates attached to these, I would just interpret this as being within this period. So
I see.
The order of them is not fixed.
I see. Okay, thanks.
I've discussed that before, but would you say officially that depending of the status of Zefiro, Lightship might be advanced or moved, or because date or status of Lightship probably depends of the achievement of Zefiro, the confirmation on that?
Yes. I mean, predictions are difficult, especially about the future, as they say. So, yeah.
Sorry for this question.
From ESA as well, Earth Observation Director. I was wondering if for Zefiro you consider as well trying different approach on payloads, and especially trying to find like using on the shelf have this quite cheap and fast instrument.
Yes. So once again, I mean, everyone likes to say we'll use off-the-shelf instruments, but every time it's going to be a custom instrument, it's a custom mission, and so on. But obviously, high heritage instruments are preferred. Yes, ESA is looking at different models for procurement.
Hi, Colin. Can you say something about ESA interests or plans for participation in human Mars missions? I don't know any.
Human Mars missions. Yes. So it's actually on your screen. The Horizon goal is to have Europeans as part of the first human Mars mission. So that is a Horizon goal. There's a lot of steps on the way to that goal and a lot of spending on the way to the goal. So these are intended to be in that direction. So developing communications infrastructure with a data relay, developing precise and heavier landing capabilities with the set of landers. Those are on the road. Yeah.
Thank you.
Sure.
Any last question? If not, I think you can thanks Colin again.
Thank you.
And next on the list, we have Kevin Nelson from University of Oxford. He's going to focus this time on TGO and tell us about recent observation of Martian climate and trace gas with ExoMars trace gas orbiters.
Hi, I'm Kevin. Thanks, everyone. Right, so I'm going to talk about the Trace Gas Orbiter. Colin introduced it pretty well. It has 4 instruments, a color and stereo camera, a neutron detector, and 2 atmospheric remote sensing suites. They'd each have several channels in them, NOMAD and ACS. The objectives are to detect any trace gases diagnostic of active geological or biogenic activity, to characterize any trace gases we find, and attempt to locate possible sources of the trace gases. We also want to characterize the water cycle on Mars and solve the mystery of Mars methane. So I work with the Atmospheric Chemistry Suite mid-infrared channel, which looks like this. It consists of a large shell grating to get us access to the mid-infrared range, coupled with a secondary diffraction grating to separate the orders which overlap in that range. It has the finest spectral resolution of any instrument sent to Mars to look at the atmosphere so far, and I'll show a bunch of spectra. ACS, several of its channels, as well as those of NOMAD, operate in the solar occultation mode, where as we come out of the shadow of Mars or go back into the shadow of Mars, we take a series of measurements looking straight at the sun, with the light from the sun passing through the limb of the atmosphere, giving us a long path length to maximize absorption. And the technique is also self-calibrating, getting us absorption spectra where we see how much sunlight is missing after passing through the atmosphere, with a really high signal-to-noise ratio. This is a look at how we sort of track our data over time. The x-axis here is solar longitude, so that's the degrees in Mars' orbit around the sun, so it's 1 Mars year. And each panel is a different Mars year. We started at LS 163 and Mars year 34, which was April 2018, and it is now LS 155 in Mars year 38. And so this is all the data we've collected over time, and it's a function of latitude. So each orbit, we take 2 observations, 1 north, 1 south, as we come into and out of the shadow in the solar occultation. And as the orbit plane precesses, you get this sort of pattern over the different years. This is a look at the major gas species available to us. On the top of the big ones, so you have the spectra, the modeled spectra of carbon dioxide, water vapor, and H2O. Again, they're absorption spectra, so if all the light from the sun passes through the atmosphere, we get 1. If no light passes through, we get 0. On the bottom is where some of the minor species are located, hydrogen chloride, ozone, methane, which we haven't seen, and other things that we're looking for. Each of these little dotted lines separates it into a different position. We don't get to see the entire spectrum instantaneously. We have to choose one of these segments so we can study really strong water lines on one orbit, and then we can go and hunt for methane on another. So again, the primary objectives are to find these rare trace gases. This is a little diagram showing some of the processes that are happening and some of the gases that we know exist and some of them that we have never seen. So on here, the yellow box HCl, if we were to update this, would be found, but we still haven't reported on any other organic molecules or nitrogen species, and we haven't been able to find sulfur species. So as a reminder, this is now a fairly dated paper, surprisingly, but we still haven't seen any signs of methane after 8 years of observation. But I do want to remind you what we see instead. Over the position where we look for methane, this big Q branch feature around 3,000 wave numbers, we found a completely undetected, unknown band of CO2 lines. On the bottom is a spectrum of data that we measured, as well as a best fit, and the top is their difference, and the little arrows point to where we actually managed to calculate the line positions. And this is now part of the high-tran line list. But that's where we hunt for methane, that's where other people have detected methane, and that's what we found instead. And it wasn't observed on Earth because methane in Earth's atmosphere is opaque. And nearby it also, we found, this is a look at ozone. So on the top is model contributions at our spectral resolution, and the bottom is a set of spectra in purple, and the black line is the average, and you can see it pretty well, and it fits really well. But we're seeing 2 to 10 times more ozone than we anticipated. And so we weren't expecting to actually be able to measure it above our noise in the spectral region, but it's there too. And both of these gases directly overlap with the particular places that we and others hunt for methane, either where you have this Q branch up here on the top left, or really strong single lines on the far right. On the one side, we have these new CO2 bands that overlap with our big CH4 branch, and on the right, we have the ozone, which interferes with the lines that we look for methane as well. What we did find is HCl. The signal it took a long time to find, but when we started investigating it, it became really clear. You get these pairs of lines of the primary and secondary isotope log in different diffraction orders, and you can see them changing with height, and they stand out really strongly above the noise. It's a really clear spectral region without a lot of CO2 and water vapor. So ozone and HCl are really interesting because they operate in completely different opposite ways. On this plot here, it's our solar occultation observations as a function of latitude for 3 different years, and the x-axis is time. And on the left side of the plot, we are in a period where it is southern fall and winter, and the atmosphere is generally really cold, contracted, doesn't have a lot of water vapor in it, and that's the time when we measure ozone all the time. And on the right side, we barely see ozone at all. And that's when it is spring and summer in the southern hemisphere, which causes the South Pole to sublimate. The atmosphere gets a little thicker, it expands, we get more dust and more water vapor. So HCl appears only in that time. HCl is positively correlated with water vapor, and ozone is anti-correlated with water vapor, and they show this complete dichotomy, which is really fun. So we've been able to use ACS to measure the anti-correlation with water vapor along the vertical. And over on this right-hand panel here, we have the vertical profiles of ozone, water vapor, and temperature grouped into different periods and latitude locations, either highlighting what happens near the equinox when we are able to see very high northern and southern latitudes and the atmosphere is fairly symmetric, to the green data that is near the South Pole during southern winter, which is where we get a strong enhancement of ozone because there's very little water vapor in the atmosphere, and it's the photolysis byproducts of water vapor that cause the odd oxygen to form an O2 bond and reduce the amount of ozone. So that's where we see the most ozone with the coldest temperatures and the least amount of water, and then some sporadic northern events, northern observations. This is a really fun thing I've been looking at. This is a zoom into one of those groupings. So it's the individual profiles. Here we're looking at the very rare times I'm able to measure ozone during the near perihelion. So this is again when it's southern spring and summer, and it's the dusty season. The whole atmosphere is warm, and there's water vapor at high altitudes at very high northern latitudes. And our northern extent during this period is limited by north polar day, so it's always sunny. There's no terminator. We can't make solar occultations, so we stick a little farther south. And generally, I can rarely measure ozone, and when I do, it only occurs in very low amounts, below 10 kilometers, when the water vapor is cooling near the surface. And then on this plot, there's this one sort of yellowy green line, and it's completely different. But I think it's real. It's very cold temperatures, almost no water vapor, and a huge abundance of ozone, and that's a sampling of the North Polar Vortex. When we can see the North Polar Vortex is really hard. This is all the data from all the Mars years together now, and you can see that the northern extent of our observations dips down as northern summer expands. And across these lines is the measured extent of the North Polar Vortex from MCS data. And that little red dot on the far top right is when our observations are inside the North Polar Vortex, but we're not at the equinox period. So I can confirm that was, in fact, a North Polar Vortex, and we're going to try and make more observations in that period for ozone. So going back to the rest of what happens in southern summer, this is a look at 1 year from, I lost the LS x-axis, but this is again time going from the equinox right before southern spring and summer to the end of summer. And you can see changes that happen in the dust lifting. You have lots of strong dust activity that picks up. The dust persists in the season until you get to about LS 320, and then you have this late season storm. And when the dust is lifted in the atmosphere, it strongly affects the temperature of the Martian atmosphere, and that raises the hygropause, and so you get this haze of ice that only exists at this cold level above the dust. And below that, we get really strong abundances of water vapor. And then on the bottom panel, finally, we can see that the HCl tracks the water vapor abundance and height very well. So looking at the correlation of all the different parameters, HCl, water vapor, ozone, temperature, ice, and dust, we see really strong correlations between water vapor and HCl. We also see fairly strong correlations with the HCl and the temperature, and of course temperature is really strongly correlated with water vapor, and that's what really drives where we get water vapor and how much there is in the atmosphere. And there's also a fairly strong anti-correlation in HCl with ice. When the ice is forming, the HCl is going away. And then to close off our discussion of HCl, I'm going to point out the thing that Colin mentioned, and that's the aphelion observations. On the top panel is zonal average dust abundance. That big orange line shows the big Mars Year 34 global dust storm and the late season storms really clearly. On the bottom panel are mostly non-detections of HCl. There are these little crosses on the left, and then once you go past the equinox at LS 180, and it's now southern spring and summer, and you get dust and water vapor in the atmosphere, we start getting more and more observations of HCl, and you get this big peak on the right side. But right at LS 100, in 3 different years, green, pink, and purple, there's a set of triangles, and those are real observations of HCl, verified looking at the spectra, and they happen at the same time. And even more freaky, they happen in the same place. This is our observations for a couple of years. Generally, when we get observations at this latitude band, it happens late in the perihelion season, but all of our observations of HCl outside of the dusty season occur in one location. And it's really, really poorly mixed. We can have observations from a few days before or after we find HCl in about the same place, and we have the same atmospheric conditions, and no sign of HCl, and no sign of HCl at other longitudes. So it's there, it's strong, it's coming fast, it's going away fast, it's really poorly mixed. And so one of the things we're sort of looking at now is the geology. That was the purpose of the instrument package on TGO with CASIS. And the area that we find the HCl in is on the flanks of the Alba Mons volcano, which is marked by all these lines. This is the Tantalus Fosse, or the Alba Fosse on the bottom side, and it's all these graben formations, these deep troughs. And we've been taking a close look at that. Daniel Mej has taken a look with all the available imagery in that area. The top left panel here is sort of a geological map of the fosse, the Alba Fosse and the Tantalus Fosse, showing all the ridges and cracks overlaid with where we're seeing HCl. The next 2 panels are high-res CASIS images. The middle one has some topography on it from MOLA, and the right one shows this sort of fissure or line that we're finding on top of some of these ridges, and the right one shows one in graben, and those are high-rise images. So we're sort of trying to figure out how there could be some sort of seep happening on these topological features. It's very much a hypothesis, but it's very, very tantalizing. And with that, I will conclude, and thank you very much.
Thanks a lot, Kevin. Any question from the room?
Oh yeah, just one.
Hey, Michael Mission at JPL. Could you return to just the previous slide? I was curious there. The yellow dots represent the the tangent point of your observation. And what is the, for lack of a better term, footprint of the measurement on the surface? You know, like if that looks very tiny compared.
It's very small. So the satellite is tracking, and when we make our measurements, like each observation takes about 2 seconds, and depending on the beta angle, which determines how long we're in the sun, those tracks get longer and longer and longer. And if you were to plot the track from our measurements from, when we're hitting the ground at less than 0 kilometers to like 200, you might get a pretty long track. But HCl only exists in the very lowest layer of the atmosphere from like 0 to 7 kilometers. So that portion of the track is pretty much, it's like 2 observations in sequence that like maybe we'll only see it in 2 or 3 spectra in the whole sequence.
See.
So where the HCl is, it's a narrow track.
All right, thank you. Yeah.
I think you need to come closer to the mic.
Sorry, I'm William from Elsie. Sorry if I don't, if I lose some information, but I understood that the HCl has a strong correlation with dust season, but in this region, yeah, that slide, the next slide, please. Yes, this one. So the detection in this region, it does not correlate with the dust season. That correct?
So it sort of does. The timing is really particular. So if you were to show, I spent a lot of time looking at plots like this and making zonal averages. This is very south, but if you were to make the same lines up here in the north, the timing at LS about 100 does correspond to kind of northern latitude peak heating. So that's where the temperatures are maximum and where the dust is maximum. So we do get some dust lifting. Like the conditions for these observations are not inconsistent with the perihelion period. There is water vapor in the atmosphere. There is some dust in the atmosphere. And everything is constrained to much lower altitudes. So it's not inconsistent. It's not like we are seeing HCl without water vapor. They're still really correlated. They still occur in the same altitude range with the same shapes. The interesting thing about these observations, though, is that when we have nearby observations and there's dust in the atmosphere and we measure water vapor and we have clear scene conditions and can go really close to the surface, there's no HCl in the spectrum, and we can verify that by looking into the data itself, which is strange. So the seepages kind of neatly explain the location, the repeated location, and the lack of variability, or the lack of mixing in the atmosphere, but the punctuality is really bizarre. But that also could have to do with something to do with the way the ice on the surface is sublimating and removing. That's sort of what we can picture, is that maybe there's some sort of trap, and when there's frosts and ices, it kind of keeps it down, and then when the summer comes out and the surface is kind of the warmest, that's when you start getting venting.
I'm at Brown University. Could you go to your global map, which shows ALBA in context? Yeah, okay. So the blue are also detections, right?
But they're in the other season. They're in the dusty season. So that's the distribution of our observations in the dusty period. And then I think the coloration, Sasha made this plot, and I think his point is that there's nothing in between.
Okay, thank you.
But we get all of during the dusty period, we get HCl kind of globally distributed.
Okay, let's thank Kevin. Oh, no, stop. Question.
One more question?
No, it's good. No, it's
come on.
okay.
Okay.
Let's thank Kevin one more time. Okay, so now we're moving to the second part of our first session, talking about liquid water and possible recently habitat on Mars. And our first speaker will be Evan Blanc from LPG Nantes, and he's going to talk us about possible glaciophygal activity in Hellas Basin.
Okay, so hi everyone. Good. I'm Evan Blanc, second year PhD student in Nantes University, and today we'll talk about a case for possible late glaciofluvial activity on Eastern Hellas Basin, looking at valley morphology and glacial signatures. So why late activity? Because we are talking about the Amazonian period, which covers the last 3 billion years and which is considered to be cold and dry with a thin atmosphere. So with these conditions, and in contrast with the Noachian or even the Hesperian period, the stable liquid water at the surface is considered as very unlikely. In fact, if we looked at the fluvial or the glacial surface alterations, they appear to be quite common for the early Mars, while it's not the case for the recent period. However, there is different geological observations that suggest that near different heat sources, such as, for example, volcanoes or even large impact craters, short-lived flow would have been possible. Other observations, such as the fresh shallow valleys, for example, suggest that those Amazonian systems are more related to, are not necessarily related, to the heat sources. In fact, recent observations show that over the mid-latitude, those Amazonian systems will have been more associated with the presence of ice, suggesting that we have subglacial or even proglacial systems. So is it the volcanism, the presence of ice, or even the climate that drives those valley formation? Different key questions can be highlighted, and notably under which climatic conditions and through which local processes could the liquid water have existing during the Amazonian period. So to answer this question, we'll focus on a study area which is localized in the Eastern Hellas Basin, and where we have specificity. In fact, we have the Hellas Basin, so that impact a lot this area, notably the distribution of the moisture and the water vapor. And as you saw with different climate models, so this one is, for example, the one of Forge et al. In 2006, this specificity will lead to enhance the ice accumulation. So in this context, the aim of the study will be to better characterize the landscape in order to evaluate its implications for the past climate. So here you have the study area with all the morphology and landscape. And you can see that we have crater rims and ejectas. We have the presence of mesas that were actually already mapped by Ivanov et al. We can see Winkle Ridge, volcanic structures, and we can see also volcanic viscous flow features, mapped by Levy et al. In 2014. Looking at the valley system and the Winkle Ridge, we can see that we have a large amount of morphology that are about the study area. So if we focus on the valley system, we can see that we have hundreds of kilometers long valleys that flow from the west to the east to the west, so generally towards the center of Hellas. And based on cross-cutting relationship and also the morphological aspect, we were able to define two types of valleys. So the first one being the ancient flow features that correspond to those valleys that appear generally dendritic, even if it's highly eroded. It becomes easier to identify them when they are directly incising the mesas, as you can see right there, forming even potential broad and low terraces. So with the relative chronology, we suggest that these valleys record ancient flow events. And based on crater counting, we were even able to say that those dissections is consistent with an Hesperian age. Another set of valleys can be observed right there, and you can see, for example, with the panel A, that they appear fresher. And actually, if you look at, they are actually cutting different ridges. The same ridges are actually cutting the ancient flow events. So based on the relative chronology, we are able to define younger generations of the valleys that were actually preliminarily dated as Amazonian. If you look at, for example, the panel 2, we have here a good example where we have two initial flow systems that are from east to west. And after the formation of the Winkle Ridge, we have the deviation of the valleys, suggesting a potential reactivation. So the aim of this study will be to better determine the origin of those most recent events. For this, we'll focus on a study case which is in the southeast part of the study area. And here you can see that we have main valleys that is quite associated with different ridges. I will try to, yes. So with different ridges, those ridges appear to be perpendicular to the valley. And if you look at this valley, we can see an abrupt source, a low sinuosity, and few tributaries. Let's focus on this study area right there, which correspond to an high-rise images, and where we can see that we have a main valley that is actually cutting two different ridges and terminating with a fan-shaped deposit. We can observe that we have subparallel channels that are actually flowing into the main valley, and if we look at the high-rise DTM, we can see that those lateral channels do not follow the local topographic gradients. Looking at the profile, they appear to cross-cut the ridges and appear to be perched around 10 meters above the main valley. So now let's try to present a spatio-temporal evolution of this system with notably a 3D view, and where we can see here that we have, first the ridges, here the main valley, and here the fan-shaped deposits. So we suggest that in this area we had a nice covering, where here we can see that we have an ice front that reflects an ice mass from the west that was retreating from the west to the east. As the ice was retreated, we have a glacial tongue that can persist in the local topographic low. This could be due to the fact that we have, for example, a subglacial channel. And here we can see that we have the presence of lateral meltwater channels that correspond to the meltwater that flow between the ice margin and the adjacent valley wall. As the ice continues to retreat, we can have multiple generations of lateral meltwater channels that are formed. And because we have dynamics and potential climate variations, we can even imagine the potential formations of moraine as the ice front remain stable. For this, for example, we have nice example, notably in Iceland, when we have a large retreat that is interrupted by short cold events, we can create such a landscape. The retreat continues with the formation of a fan-shaped deposit, and here we have a nice example, notably in the margin of the Russell glaciers in the southwest Greenland. And in this photo that is actually taken by Anna Grogaloff, we can see that we have a moraine deposit right there, a nice front, and we have here a fan-shaped deposit. Then let's focus on the lateral meltwater channels that can also find potential analogs. And for this, let's go in Devon Island, where we can see that we have a landscape that have been carved by many generations of glaciations. And in fact, looking at the valley, so here we have a past subglacial channels that is actually related with different lateral meltwater channels. So here in this valley, we can imagine that we had before glacial tongues that were present, and we had the presence of lateral meltwater channels. Those ones actually reflecting the direct margin positions of the ice mass. So after the retreat, we have a series of oblique channels that are present in the landscape that are quite straight and that appear to be, if you look at this profile, perched on the valley side. So let's go back on Mars, and here in this study area, we can propose that we have a glacial assemblage that is consistent with an ice margin. If we look at, for example, the fact that we have an ice flow that is consistent with the regional slope, the fact that we have the presence of the fan-shaped deposits, and also the presence of the lateral meltwater channels. So in this context, we can even discuss with the ridges and saying that it's potential moraine deposits. So let's come back to our initial mapping, and I present you that we had different ridges over the study area. And in this context, if I just said that some of them can be present as moraine, others, as you can see on these figures, appear to be more dikes, so they are very straight. And another aim of the study will be to define if it's either a moraine or a dikes. And for this, we use different criteria of confidence that I will not have time to present you today, but we obtain a result like this with this mapping, where we can see here that we have in red the higher confident dikes, and in blue the higher confident moraine. With this mapping, we can do some spatial correlation, and notably between, for example, the moraine and the recent valleys, where we can see that we have quite close correlations, and we can ask us some questions, notably, are they formed synchronously during the Amazonian? About the dikes, so they are quite long and appear to be very present in the study area, and this highlights that we have potential volcanic activity in this region. And let's now go back in a broader scale to see that in fact we have the study area that is part of the West Prométhée Terra, lying directly with the broader CHVP, so the Circumellus volcanic plain, which is a complex volcanic region that was reactivated actually 1 gigayears ago. In our study area, these reactivations can be maybe reflected by those fresh intrusions that you can see right there, but also right there, directly connected with the, what we call the dike. So with all these observations, let's try to propose a synthesis and interpretations of the different events in the study area, where initially we suggest that we had an ice mass that was covering the area, and that can be potentially associated with need sources. So it could be the potential dikes, the presence of intrusion, or generally geothermic or volcanic heating that is due to the regional reactivations. With this, we can suggest that we have a basal meltwater, that were suggesting, flow that is under the ice sheet, but also over the ice sheets, and creating different glacial assemblage. Different processes are in place, notably the ice retreat, but also the fact that we have waters that flow over hundreds of kilometers. At the end, we obtain this landscape with different intrusion, dikes, moraine, or even fan deposits. And this suggests that we have a glacial assemblage reflecting a nice margin, retreating, and so suggesting that we have surface and subglacial liquid water present in the study area. Different questions can be highlighted, and notably about the atmospheric conditions in place to have this basal meltwater and water flowing over hundreds of kilometers. And notably, did the climate conditions make it possible to allow this surface liquid water to remain stable at such scales, so it could be below or even beyond the ice sheets? So let's now try to conclude. We have evidence for regionally extensive liquid water activity potentially related to glaciations or even volcanic activity during the Amazonian in this region. And the extensive scales of the system suggest that we have a climate component. So that's why we are here today in Martian time in order to explain those observations from a climate perspective. Thank you.
Thanks, Evan. Any question from the room? Please come to the mic.
Hi, Bruce Tchaikovsky, University of Colorado. Pardon my ignorance as a geomorphologist, but I'm curious about how you distinguish between moraines and dikes. When you showed the map that had both of them, dikes and the moraines were all subparallel to each other, and is it just coincidence?
For example, we did a field trip in Iceland to see different moraines, and we elaborate so different criteria. For example, the asymmetry, the fact that you have sinuosity, that is quite hard to obtain, for example, with dikes. The fact that they are very straight, or this kind of criteria. I have actually a list of this. But in fact, it's a big coincidence that is quite annoying for me to elaborate, but it's like this. But thank you.
Thank you.
Thanks for the talk. I have two questions. You say they're Amazonian. Is it possible to constrain their age more? Do you know if it's late or middle or early Amazonian?
Actually, the idea that we had that we did some relative ages, and because we had volcanic reactivations around 1 gigayears ago, we estimate that it could be related to this. And if we follow our crater counting, we also see that we have a resurfacing event that is around 1 gigayears ago. So I would say 1 gigayears ago.
Okay, thank you. And then thinking about the work that was presented yesterday about the mineralogical characteristics of polythermal glaciers, have you looked into that for this location?
Sadly, I think the area is actually covered by a kind of mantle, and so I will not expect to see anything.
Okay, thank you. Thanks.
Jim Head, Brown University. Just another comment about as we've discussed before, the details of the climate interpretation. The Fast Ticket Head, I think 2017 paper, we showed that because of the slope going down into Hellas, you can also get shear heating, melting. So there could be some component of that too.
Thank you.
Any last question? If not, I think we can thank Evan one more time. And our last speaker before the coffee break, so if we're late, it's going to be his fault. It's Lucas Lange from LMD. He's going to talk here about possibility of melting water ice to initiate and promote gully activity during recent wars.
Thank you very much. So today I want to review all the processes that could lead to the formation of liquid water on a recent past of Mars, and by recent I mean in the last 5 million years, and the possible implication for the Gully's activity. And to start with, I just want to focus on the fact that the possibility of having very recent liquid water was highlighted by the discoveries of gullies, notably these very young features that we talked about yesterday. At the beginning, most of the people think that gullies were formed by liquid water because of the analogy with gullies on Earth. But then, because of the current day activity of CO2, and we know that today there is no liquid water at the surface, then some of us have suggested that these gullies should be formed by CO2 ice sublimation, for instance. So yesterday we talked a little bit on the CO2 processes, and today I want to focus on the liquid water processes. And when we think about melting water ice or having liquid water at the surface, we generally refer to the triple point, to the phase diagram of water on Mars. Here I show a plot made by Aberle et al. Showing that on present-day Mars, given the total pressure and the temperatures, there is a narrow range of conditions on which liquid water could be stable. And generally, what is a common mistake is to just use this condition to highlight where ice could melt or not. For instance, I refer here to the last paper claiming that gullies were formed by liquid water in a recent part of Mars, where some of the authors, mapped on Mars at obliquity 30, 35, where the surface has higher temperature than 273 Kelvin and a total pressure of total pressure which is higher than 6200 Pascal. And why is it a mistake to process like that? Because first, this diagram shows you only that if liquid water is present here, then it is stable. It does not say whether or not you have melting. First, you need a source of water at the surface, and notably water ice. Second, in most studies, like for instance this one, the authors use the total atmospheric pressure. But what matters is the vapor pressure at the surface. And we know that we have a much lower amount of water vapor in the atmosphere compared to the total amount of CO2, for instance. And finally, generally one mistake which is made is that, for instance, here we use global climate models, which has a coarse resolution, to look at the surface temperatures, but the gullies, water ice today are found on cold traps, which are generally colder and not reach high temperatures as 273 Kelvin. So if we want to look at the question of having liquid water at the surface and allowing melting at the surface, we really have to dig into the physics of the melting. So, for instance, let's consider that we have water ice on a slope. For instance, we will assume that we have clean ice, and the ice is opaque, for instance. So we have first the solar flux reaching the surface. We have, again, infrared flux coming from the thermal emission of the atmosphere, reflected fluxes both at visible and infrared wavelength from the surrounding surface, and then flux from the subsurface through conduction. Then we have the radiative cooling. And finally, because of wind and the convection induced by the molecular gradient between the water vapor from the sublimating ice and the CO2 atmosphere, it triggers the sublimation of water ice. And the key question is, can this ice melt or not? Well, if we just look at this energy balance, only with that, so all of this flux I presented, and for instance, we made the thought experiment of having water ice at the surface, at the equator, then it appears that we could have melting indeed, just based again on this surface energy balance. During the afternoon, the ice can reach temperatures as high as 273 Kelvin. We neglect the latent heat of fusion here, and therefore melt. But we miss a key physical processes here. When we have sublimation triggers by either the convection of H2 in the CO2 atmosphere or the near surface winds, you have a sublimation cooling. And this sublimation cooling is significant, and we must consider it when we address the question of liquid water and melting on Mars. It was shown by Ingersoll in 1970 in a pioneer paper, where they showed that the sublimation cooling, when you reach almost 0 degrees Celsius, is super high. It can be higher than 1,000 watt per millimeter square. And this is higher than all of the incoming fluxes at the surface. So you lose more energy than you received when you are close to 0 degrees Celsius because of this sublimation cooling, and therefore you cannot reach the melting temperature of water ice. And indeed, if we include it in our thought experiment, then the sublimation cooling is super significant, like you lose 20 Kelvin. The maximum ice temperature is almost 255 Kelvin. So we must include that when we are dealing with the question of liquid water on Mars. Yet, in this paper by Ingersoll 1970, the computation of a sublimation flux was made on a simplified model, and notably, this author assumed a dry atmosphere, but in the reality, the sublimation flux and thereby the sublimation cooling is proportional to the gradient of humidity between the surface and the atmosphere. And therefore, if we have large humidity, perhaps we can mitigate this sublimation flux, mitigate the cooling, and possible allow melting in a recent parts of Mars. So we reinvestigate this question of melting water ice at the surface using the Mars planetary climate model that now you are known, plus a slope parametrization, which allows us again to simulate the cold slope microclimate where water ice is found today on present-day Mars, but also past obliquities. And for instance, I will present here some simulation performed on present-day Mars and on high obliquity, 35 degrees, when the atmosphere was much wetter, as discussed yesterday. So for today, we use the model, and for each day of the year and each location in the model, I extract the maximum water ice or frost temperatures. So here you have a distribution of all of the temperatures normalized, and you see that we had two peaks in the distribution. The first one is around 160 Kelvin. It is in fact a diurnal water frost forming at night and subliming during day. It is super thin, so it disappears almost instantaneously when the sun hits it. So this is why you don't reach high temperatures. And then a second peak, which is seasonal frost subliming, and the maximum temperature what we generally have is 230 Kelvin. So it's too cold to melt on present-day Mars. Then, if we looked at past climates, for instance, an obliquity of 35 degrees and a solar longitude of perihelion of 270, the humidity is higher, so the sublimation flux is lower because the gradient of humidity is lower, but still it is not enough to reach very high temperatures and be close to the melting point of water. And then in the best case, in which we have an obliquity of 35 degrees and a perihelion which is constant with the northern summer, the humidity is super large, 217 precipitable microns on average on the planet, and we have really high temperatures like 260 Kelvin, and the maximum is 270 Kelvin. So I tested a lot to be sure that it's not just a numerical effect, but yet you never reach the melting point of water. And this means that when we have frost at the surface or ice at the surface, the sublimation cooling is so important that even in past climate, it does not allow to have melting. So then the second possibility is to protect the ice from sublimation by, for instance, a lag layer. In this case, the ice is protected from the sublimation and the sublimation cooling is reduced. Yesterday we saw that we have wider spread water ice in the subsurface of Mars, exposed by impact craters or detected by neutron spectroscopy, for instance, and we can see whether or not this ice, for instance, can melt or not. So to do so, we use again the planetary climate model and compute for each of the simulation performed the depth at which ice is in equilibrium with a near surface water vapor content, and we compute again the temperature experienced by this ice. And here are again the distribution of the temperatures on present day and obliquity 45. The LSP is 270 in the part of the middle and 270 on the right. And again, as you can see, we never reach the melting temperature of water ice. Why? Because generally, when ice is in equilibrium with a near surface water vapor content, it is at depth and never heated enough to allow melting. Generally, it's too deep to be heated, so we can never again have melting. So if we just briefly sum up, if ice is at the surface, the sublimation is too strong, the sublimation cooling is super strong, and we can't melt. If ice is in equilibrium, if ground ice is in equilibrium with a near surface water vapor content, it is generally too deep to be sufficiently heated and allow melting. So the best case actually would be if we add by a mechanism ice exposed or almost protected by a very thin layer or dust of regolith and bring back close to the surface and being heated. This is a mechanism that happened on Mars today. For instance, the impact craters detected by Barn et al. In 2009 exposed almost clean ice at the surface of under a very shallow, thin layer of regolith. And for instance, in the formation mechanism for gullies proposed by Pierre-Simon and Forget in 2016, the sublimation of a slab ice of CO2 would remove the superficial material and almost expose the ground ice to very close to the surface. And therefore, the key question is, in this base scenario, melting could occur. And again, this scenario proposed by Pierre-Simon and Forget also happens already. For instance, as shown by Bethany earlier this week, Currer et al., for instance, proposed that there is some exposure of water ice in the gullies alcove on present-day Mars today. So we aim to simulate this kind of best-case scenario on which ice could melt or not. So we developed a 1D model to simulate the thermal condition when such a process happens, so when there is a removal of surface material on a slope, and therefore if ice can melt or not. And here are the key results for, again, present-day Mars and past climates. Here we have tested by putting ice out of equilibrium at several depths on the slopes. And as you can see, when ice is too close to the surface, so when you're on the left, on this plot, the sublimation cooling is again super strong and you have lower temperatures. When you go at depth, ice is again too deep to be warmed and you cannot bath. The best scenario is when ice is just protected by a very thin layer of 1 or 2 centimeters. And actually, you can show analytically, this has been made by Schorghofer in 2020, but the best case to melt ice is when you have a lag layer of 1 or 2 centimeters protecting the ice. But then again, it's not straightforward to reach the melting temperature of water ice. It depends on a lot of parameters, and we have identified 2 key parameters controlling that. The first one is the diffusion coefficient of water vapor in the lag layer. And for instance, here you have a distribution of the ice temperatures in our simulation for 2 kinds of diffusion coefficient. The first one in gray is a typical value as shown by, for instance, Hudson et al. With lab experiments. On the top panel, you have a distribution for present day. And on the bottom panel, you have a distribution for the obliquity of 35. And our experiments show that if we want to reach temperatures higher than 273 Kelvin, we need to have a very low diffusion coefficient, and this is consistent with a material which is like packed dust, for instance. This packing could have occurred, for instance, if the ice is buried below a few tens of centimeters of dust, for instance, and therefore you have a gravitation packing. So this means that, in fact, ice must be initially at depth and must be old. But then the second key parameter is the thermal inertia of the ice, and therefore its grain size, porosity, and so on. And if we assume, for instance, a thermal inertia of 160, which is pretty large, meaning really clean ice with large grain, then we never reach the melting temperature of ice. If we use a thermal inertia of 800, then we can have some cases where we have melting. But then there is a contradiction, because the thermal inertia of 800 is snow being transformed to ice. And in the first experiment, we showed that if we want to have melting, we need to have ice which is initially old. And this is the main contradiction. We cannot have, in all of the simulation we have performed, consistent assumption. In each case, it relies on contradiction. In each simulation in which we have melting, it relies on assumptions which are not consistent between each other, and we never find a framework in which we have melting. So this actually showed that in all of the possible situations which could trigger melting on Mars, well, we cannot have liquid water forming, meaning that it is very unlikely that gullies are formed by this mechanism. I don't talk in this presentation about the effect of salt and possible formation of brines. Just a short answer, if you want to really significantly decrease the melting temperature of your ice, you need a very large amount of salt, and actually this is not consistent with the presence of the amount of salts measured at the surface, possibly not at the subsurface, but really at the surface. And then there is the last case in which we could have melting in dusty ice, in dusty snow, for instance. While there's many unknown on the past dust cycle, the amount of dust that we would have in a snow mantle, for instance, at high obliquity, and the work that have been performed so far, for instance, by Clough et al., Julian et al., and so on, only relies on some very specific cases. So this is ongoing work, for instance, performed by my colleague Adi Kuller, and is the next step in this question of whether or not dusty snow could melt or not. But so far, we can just say that clean ice cannot melt today and in the recent past of Mars. If you want more information, you can look at the paper that we just submitted in general, and I'm happy to take any question.
Jim Head, Brown University. Thanks for incredibly comprehensive treatment of this. A really complex problem. I think everybody agrees that the CO2 mechanism is really clearly going on, no question. So keep up the search, and we'll see whether it's all one or maybe a little bit of one and mostly. Thanks very much.
Thank you very much.
I'm Voss, LMD. I have two questions. Sorry, Bethany. The first one is, you mentioned it in the end, but what happens if you decrease the albedo of the ice? It's very easy if you add 0.5% of dust or something like this, and ice is, of course, not pure. What would it cause, and how it will affect your results? And the second one is, what about just seasonally melting, or a very thin film above the ice? You don't need to reach all the way to melting, but you can create thin films in temperature close to the melting point.
Okay, so for the first question, we actually made the sensitivity experiment to varying the albedo. And in fact, it's a balance. When you lower the albedo, you have higher sublimation rates, which will, again, induce a strong sublimation cooling and never allow to have melting at the surface. For the second question about having thin liquid water, again, you need to reach these very high temperatures, but you have a so strong sublimation cooling that you can never reach these temperatures. Perhaps you can have thin liquid water forming if you have, for instance, a contact between the salts and the ice crystal, but this would be very thin amount of liquid water, and this is something that actually we are looking at with some colleagues, Vincent Chevrier and Edgar Riviera, for brines, but for just pure liquid water, this seems very unlikely.
A comment? Thin films can be also at 250. It just depends on the size of the film. So.
Yeah, exactly. But again, this would be very small amount, and here I was mostly referring to large amount creating gullies, for instance. But yeah, I agree for that. Yeah.
Very, very good work.
Thank you very much.
Yeah, so Bethany Ehlman, University of Colorado. Thank you again for the presentation. So, I mean, I agree on the importance of sublimation cooling, but I think I would really emphasize the last 2 points that you have here on the slide, which are salts and impurities within the ice, because I don't think there's a single ice slab anywhere on Mars that is pure. I think that's a fantasy ice. That ice doesn't exist. The ice is going to have impurities within it. And so I think considering the radiative properties within the ice in terms of where the impurities are placed, whether they're at the surface versus beneath the surface, is critically important, because even we see on Earth in Antarctica today, in lab and other places, that when the impurities are within the ice, it greatly facilitates the melting. I'm not sure I think I don't agree with your second point regarding the salts in soil, because there's plenty of soils that we have seen that do have salts that would depress the freezing point when they're adjacent to an ice grain. So I really encourage that in the future work that the focus be on the role of impurities.
Yeah, I totally agree with you for the fact that so far, like we are making big improvements step by step on our understanding of physics of water ice, and I think yes, indeed, the next step for us would be to include actually the microphysics of the ice, and notably the effect of salts, the effect of impurities on first the metamorphism of ice, how we can go from snow to ice, and then after that, introduce more complex models, notably snowpacks model, for instance, to see whether or not the solid state greenhouse effect could trigger melting or not. I think I totally agree with you. This is the next step in the next, I think, 5 years, and there are plenty of people looking at that right now, and it's a good thing, I think.
Hi, Bruce Tchaikovsky, University of Colorado. Excellent talk. I really appreciate the focus on the phase diagram of water, and you brought up points that I think very few people in the community who talk about liquid water really appreciate.
Thank you.
In terms of total pressure versus partial pressure. I've been wanting to write that paper for a decade now. Clearly now I don't need to because you're doing that. I want to pile on, though, on this issue of what you've done versus what conclusions you reach and the role of thin films or impurities. Your first conclusion up on the screen, water ice melting is very unlikely. I think that's correct for the scenario you've described. An additional problem is getting the ice there and getting it there more than once in sufficient quantities to be useful. But I think the second sentence of your conclusion, gullies must be formed by dry mechanisms, is not supported. I think there are possibilities for thin films, especially with deliquescent minerals, where liquid water is stable in the current environment. I think that's been demonstrated. And other possible impurities, the difficulty of getting water ice into the ground at any of these depths rather than having it placed there by some Maxwellian demon who comes with a small, really tiny shovel. So I don't think the final word has been said here. And in particular, I'd like to hear a lot more discussion about the role of deliquescent minerals and thin films.
Yeah, I think again this is the next step. Like again, when we have been thinking, I think for the past 20 years about melting, we have always just think of pure ice or maybe snow and so on, but we never dig into the microphysics, the effect of impurities, and again minerals. I think there's more and more people working on that. I'm thinking of Anna Sizemore and Mike Mellon looking at that in Antarctica. So I think we are starting to do that in the dry valley of Antarctica, and the next step is to do that on Mars. So I think the community is going on that. This is the next step. So far, the conclusion we made are based on the assumption of pure ice, which is again not maybe realistic for all the scenario happening, although we have clean massive ice sheet on Mars as highlighted. But again, and this is step by step, I think, and it's the next step for the community.
And I don't want the fact that there are next steps to take away from the real significance and value of what you've done so far. So thank you.
Thank you very much.
Jim Head, Brown University. I just want to add to the comment that Bruce said. We do know that, in fact, where the ice comes from, that there is ice there, because these are virtually all these gullies are in the area where below those in the crater we see definite glacial landforms and sublimation products. So a good way to go is to combine the geology and where the source might be coming from on the crater rim, et cetera, and look into that and see if there's any kind of sense of what the ice might be when it's sublimed and leaves the residue. So that's another avenue of research. Thanks.
Yeah, I think we have started actually with the models, for instance, the PEM and so on, we have started to track now the deposition of ice and sublimation, it's burying through time. But I think the key next step is the transformation from the snow to the ice also, to really track the evolution of a snowpack and then the possible effective impurities or not, and so on.
No, I think we've done a couple papers on this, Fern, essentially the transition to pure ice. So I'd love to talk to you about that after.
Okay. Hello, dear Cotter.
So I don't have a question, but I want to emphasize the fact that about the solid state greenhouse effect that could allow melting, it's very tempting. I would dream that it will work. But it's important that this has been studied already. I think we can improve the model for fundamental reason I call detail. But what has been published already show that it's difficult. You have to look at the tables, the results. It's not easy at all. It takes a very precise combination of parameters in a theoretical model, and you realize, okay, if you really have to have all that, it's not easy. I think we must revisit. It's something for us. We discussed that with Luca, because we have tools now that could with all that, it could make sense. But it's not that easy. It's important to look at the published paper. The second point is, in fact, response to you, but it's more a question to maybe people in the room like Suzanne, or because you say, well, I think the CO2 origin is done demonstrated, but if you look and you believe the analysis that shows that you have currently on present-day Mars new part of gullies forming every year, not much, that looks like exactly like gullies. When it's minus 130, when CO2 ice sublimes, why do you think you have millions of years to create the gullies? Why needing liquid water? It's hard. We are on Earth. We like liquid water. I dream of liquid water. But so the question is everyone convinced that CO2 ice right now? You don't believe the images from high rise with new gullies formed by CO2 ice? Why do we need to add water on that? Is the formation rate of gullies not sufficient? Do you have a fundamental reason, except that gut feeling that water should be there? It's so nice. It's a question for you.
Tough one.
I don't want to take away from the speaker at the podium here. I think there are plenty of instances where CO2 ice is the former of the formation mechanism of the gullies. For example, on some of the dunes, where you can have some nice carving into the sands. I have, no issue with that. I think some of the problems were those that were well talked about yesterday in terms of the larger debris, boulders, the sheer volume, the fact that the frost at the surface, I think, cannot go, tens of meters down in some cases. So I think there are morphological reasons why some sort of slope instability within the ice snowpack is important. I think, though, that one thing in Lucas's work that I just really do want to poke back on is that assumption of pure ice. I don't actually think that it's special pleading to model a solid state greenhouse, because I think that reflects the reality of what ice is on Mars, that it is not a pure slab, that it is ice that includes portions of dust, it includes portions of sands, it includes portions of salts. So it's actually a complicated, heterogeneous medium rather than 100% ice. So it's not to say that it's not challenging to melt ice. I actually agree with that. But every time the temperature starts to get to about 260 or so, there's a lot of salt on Mars that acts as freezing point depressants at that temperature. So it's actually really a call to sort of embrace the complexity of what the ice is, which is this heterogeneous slab of materials, which I think is what Lucas was saying is the direction of the future work.
And I think it's the perfect timing right now, because a lot of models are also preparing stuff for the exploration of icy moons, where there's a lot of salts across the surface. And I know that there's some models preparing, like one made IGOPS in Orsay, stuff like that, preparing for that actually. And I think we should take their experience from Earth community in the snowpack modelings to look at this new question. I agree with you.
If I could add one small sort of note from a geomorphology and experimentalist kind of point of view, I would say let's also put the water discussion for the gullies to the same type of scrutiny we do for the CO2 hypothesis, because of course we should be able to prove, and we're working on that, and part of our current work does that it's possible or impossible for these cryoclastic flows to carve gullies on a longer time scale, to erode really large volumes of material, because we see that happening. And if we extrapolate that over time, what does that mean for longer term formation? But I think the same thing we should do for the amount of melting or the amount of liquid water that is available in specific case. So I would highly, I'm anticipating with high anticipation the work that you're doing, including impurities and seeing how much water is available. But from a terrestrial point of view, there needs to be a lot of water in the landscape for debris flows driven by liquid water to exist. You can't just have enough water to make the thing. The rest of the gully needs to be saturated because otherwise you also can't get mobile enough flows to make it. So I would just say, if there is snow melt, I'm happy to believe that in the past, but that needs to be enough. And I think just saying, oh, there can be melt is not enough reason to hold on to the hypothesis per se that wet debris flows scarf these things as well.
I agree. When you look at the quantity of liquid when there is snowpack melting, it's very low and not low. Actually, it's discussed, I think, in Cotard et al. Paper, maybe. The amount of liquid water generated is not enough to generate a debris flow.
Yeah, and we also need to think about when that water melts, because maybe over a season it could be enough to produce a debris flow, but that doesn't mean that in that moment it produces a debris flow, because it's a quick thing that happens. So during one day, we would need to have enough water in the system. And especially with the Martian nights being so cold as well, if it then freezes all over during the night, you lose that saturation in your soil, in your gully lower down. So.
Two quick comments and one question. The quick comment is first, it's a little misleading to the way you presented to say that we assume pure ice. In fact, what we assume is that the sunlight is absorbed on the opposite, near the surface where it's conducted directly to the surface and radiated away if you want, or it's warmed directly. So it's not absorbed deep enough. So it's the opposite of saying it's pure ice for relatively. The other comment is, again, it's not the question in some way is not to know if it's feasible that CO2 ice can create gullies. In some way, the question is, are the gullies that we see forming today real gullies? If they are real gullies, we just have to accept that CO2 ice can make real gullies. If not, then there is a geomorphological debate. Are these real gullies? And my last question is a question for the community. It's a question that is there. It's to in ice that is formed by precipitation in the past, how much salt can you put in that? And I remember it was a big debate we had years ago, Gullies meeting, I think it was in Houston in 2009, and it was a big debate. And lots of people were saying, you can't put salts in snow, but because you need a lot of salt to decrease the temperature of melting. A little bit is not enough. You have an opinion on that?
We have been discussing with Anna yesterday at lunch about that, I think about M2020, they are looking at using, I can't remember the name of the instrument, but they are looking at the composition of dust and trying to quantify actually if there is salt or not on the dust grain at microscale. And then we can use this quantity to assume quantity of salt in the snow as the dust acts as a condensation nuclei. Possibly like that's an estimation we can use. Thank you very much for coming for the liquid water round table.
Okay, thanks. Lucas, one more time. Okay, so it's the time for the coffee break now. I think we can get a last round of
Okay, so a couple of announcements while you're sitting down and getting ready for the session. One of them is standing up there, so there will be an informal session at Ground Control. If you don't know what social event this evening at Ground Control, as mentioned here, if you don't know what Ground Control is, it's a place, and you can ask Aaron all about it. He lives there, basically. And another... Aha! So you have to answer now.
It's a big place. You don't need to order a place. You can have many kind of different beers or snacks, and it's a big. You have indoor and outdoor seating location. It's on the 12th, but it's not very far. I think it's like 2 metro stations, or maybe 30 minutes by walk, or 10 minutes by bicycle, or 5 minutes by cab. Choose your own preference.
And the other announcement is for this noon. You remember Olivier Bessac mentioned that for those who want to see the excellent mineral collection in Jussieu, he'll be waiting for people at 1:10 p.m. So it will be a short lunch break for those who go there. It's at Tower 25, just really walking distance, like not even 2 minutes. That's it.
So, hi everyone, my name is Yann Senior. I will chair this session. So firstly we'll talk about the last part of the liquid water and possible habitats recently on Mars session. And first presenters is Jacob Adler, who will talk about Mars paleopressure through laboratory sediment flow experiments.
Thank you. So today I'll continue talking about some lab experiments that we can apply to our remote sensing interpretations and to our modeling. Specifically, I'm looking at sediment flow deposits. So these sediment flow features have occurred on Mars across space and across time. And they can provide constraints on water activity, and we do use them all the time to provide constraints on water activity and past habitability. But there's still a lot of assumptions, there's still a lot of uncertainty. For example, on the left you see potential mud volcanoes. These are still debated. Are they mud? Are they igneous volcanoes? Large-scale mud flows or lava flows, right? And so we have a lot of uncertainty. Even with the best climate models and remote sensing data, we can still have a difference of opinion. But what can we do with lab experiments to help us constrain our interpretation? So the driving science questions that I focused on are, firstly, what range of morphologies should we expect to see for sediment flows under realistic Mars conditions? Secondly, there's some prior work with really shocking results. One is that mud can boil on modern Mars and levitate. That's shocking. The other is that mud can freeze and form morphologies that are hard to distinguish from Pahoehoe lava flows. Also shocking. But is this true for other compositions, like a bulk Mars composition? Is it also true in the Noachian and Hesperian? Finally, the third driving question is, under what Mars climate conditions should we continue to use Earth analogs for these features? So to address this, we headed to the Lars Dirty Mars Chamber at the Open University in the UK. You might have seen this setup before. We used a test bed where we did sediment flow experiments on a simulated Mars surface. And I'd like to point out that our reservoir of Mars mud, which is made by combining deionized water with different Mars simulants, is a blender. And it's important to use this mud reservoir as a blender because we want to make sure that grains don't settle out of suspension and that we keep the mixture homogeneous during pumping out of the chamber before our experiments. The parameter space we're testing is actually quite large. And so one parameter is pressure. You can see on one of these axes. And we can control that. In our experiments, we performed from 5 millibar all the way up to 1,000 millibar. And this represents, right, going back in time on Mars with higher pressures in the Noachian. For temperature, we can achieve temperatures as low as 246 K and as high as 295. We do that by freezing a copper plate in the entire test bed overnight to get really cold temperatures. And for viscosity, what we do is we change the ratio of water to sediment. And so what do we get? Well, we've collected over 1 terabyte of data. It's a lot of data. You can actually download it all. It's on Zenodo now. And so we did about 79 experiments. And for every experiment, we've logged pressure every single second and temperature every single second. That temperature comes from 3 different places. So we have the atmosphere above these flows, we have the test bed temperature, and then we also have the temperature in the mud reservoir. We take thousands of photos in total, and every few hundred photos we can make a nice high-resolution digital elevation model of our deposit to study later. So that 4th parameter in this big parameter space we're studying is simulant composition. And we tested a lot. So we tested some commercially available options first. MGS-1 is a global Mars simulant based on the Rocknest site that Curiosity investigated, one of those soils. And then also we asked Exolith Labs to give us a basaltic version, which is essentially just the first 4 components of that, so that we can tease out what minor constituents really do. But we weren't satisfied with that. We wanted more basaltic controls, so we bought another commercial option, which is a basaltic powder from a single source in Canada, and also we made our own in-house from Columbia River basalt. And we wanted to match the grain size distribution that we thought was relevant for Mars. So this Georgia Tech Basalt GT and Basalt GG vary a little bit in the grain size. Finally, we wanted to answer the question of, okay, if you spike clays in different amounts, what's going to happen? So we used a swelling clay, which is a bentonite, and a non-swelling clay, kaolinite, which are both found on Mars. And finally, we wanted to answer the question about what do salts do? So here's a little video that shows exactly what I'm talking about. So we're at the Mars chamber, and PhD candidate Sharissa Thompson is doing the pull, which basically turns the mud reservoir and starts to pour the flow. So now I'll show you some high-level results, and I can't talk about all 79 experiments, but what I'm hoping to show you here is just the difference that you can take away between experiments on modern Mars, where you see flowing over a cold surface, and then in the middle panel, you will see boiling, which is modern Mars, maybe in the afternoons, but places where the surface temperature is a little higher. And then finally on the right, Earth for comparison. So I'll let this video play, and then afterwards I'll narrate what's going on. As you can see on the left, freezing is very different from boiling, which is very different from flowing, right? These are completely different end members for flows, and I'll show a few more examples. But the high-level takeaway here is that the phase of the mud is changing. The phase of the mud determines the rheology, the flow physics, and that determines the deposit morphology. So on the left, you see things like an icy, muddy crust forming. You also see trapped bubbles, cavities. You see the 4 different things that are also found in Pohohoi lava flows. So we confirmed we saw inflation, lobe formation, the steamroller effect, also an insulating crust. In the middle, you see things like boiling. This is very energetic, so you have intense vaporization all around, including the bottom of the flow, which creates the Leidenfrost effect, and also forms levees around all of the warm bed experiments. You have enhanced avulsion, which would lead us to find multiple lobes instead of single lobes. And by comparison, on Earth, you mainly see a single lobe with mostly laminar flow, what we would expect from flowing mud. So let's quickly see 2 different examples. And this one is spiked with a little bit of kaolinite clay, but I'm not going to talk about the differences in this talk about that. The point is that the general trend, MGS-1, which is a commercially available global Mars simulant, freezing, boiling, flowing. Pretty different morphologies. So how can we sum this up and how can we use this information? Well, at pressures above about 20 millibar, I'd say that the changes are pretty subtle. There are some trends though. If you look from 20 millibar all the way up to 1,000 millibar, the flows are getting longer and thinner. However, how would you notice this on Mars? I'm not entirely sure if you'd be able to pinpoint these subtle differences. But below 20 millibar, that's where the crazy stuff happens, right? The changes are extreme. So as you're dropping in pressure from 20 down to 5 millibar, so think the Amazonian period, you have intense boiling or you have intense freezing, and in some places on Mars, you might just have the flowing option. And so these Amazonian deposits are perhaps more often multi-lobate. They're probably longer due to the Leidenfrost effect, and there's these unique member morphologies that I'll talk about. And so just as a review how this Leidenfrost effect works, our collaborator Peter Broge back in 2020 showed an example of basically the outgassing underneath the mud if the surface of Mars was warm would cause the mud to levitate and form these levees. So some interesting boiling morphologies. You can see in this snapshot from a video a large bubble about to burst. This leaves behind craters in mud flows or cavities, voids. Intense sputtering of sand grains, and this creates levees along the flow perimeters of all of our warm bed experiments. There's ruffles, so this is where sliding occurs due to the Leidenfrost effect, and then you have this back propagation once that stops and creates the ruffle. And then finally, enhanced erosion. This looks really similar to amphitheater valleys and multi-lobate flow, which you don't see in the other scenarios. Finally, even if flow is not on the surface, but mud is in the subsurface, we might see a surface expression. So if the conditions are right and boiling occurs, then you might get this buildup of a cone. It's basically a levee, but around all sides of subsurface mud. Freezing morphologies include rounded lobes, ice sediment separation, vertical breakouts, collapsed voids, ice lensing, which could be very useful for comparison to large-scale features on Mars where we've already seen this, for example, potential pingos, and finally warping. So let's go back to answer those main driving science questions. The first one, so where and when on Mars? To do this, what I did was I used this awesome tool, the Mars Climate Database, and I produced 16 different maps. So there's 8 pressure, and this is the pressure at the surface, and surface temperature maps, just as a general approximation. And then I combined all of these data points into the distribution that you see circled on the right. So this is the pressure temperature diagram of the entire map of Mars throughout the year, right? And we're looking at 8 time points. So there's morning and afternoon, so 5 a.m. and 1 p.m. In spring, summer, fall, and winter, right? Now, how do we get to the Noachian? Well, I estimated, and all I did was I took the pressure values and multiplied them by about 100. So the final task, though, is not to look at water, because these flows are not just pure water. They're our Mars mud that we made. So how do we do that? Let's zoom in here on the triple point, and I will show you. So remember that we logged pressure and temperature every second in our mud reservoir, and this actually follows the phase diagram of our mud. So we took about 40 experiments that didn't have the salts or clays added to them and plotted them here, and what you find is that as pressure drops vertically as you're pumping out the chamber, eventually you reach this point where it follows its vaporization curve, and it essentially maps out the phase diagram of our Mars mud. And so in summary, the triple point is moved slightly downwards and to the left, but it's largely similar to pure water. So we used our phase diagram of mud that we experimentally determined and plotted back on Mars where you'd expect this different type of behavior. And so in yellow you see boiling, in teal you see flowing, and in purple you see where the conditions would be conducive to, if you had a feature like this, where it would freeze. The point here is that today in the Amazonian, this unique behavior happens in the afternoons where all of the morphologic end members are possible. But in the morning time, as been mentioned earlier, mud always freezes. It's always going to be frozen. It's too cold in the morning. Now, what happens if we go back to the Noachian? If we multiply the pressure by 100, we see very similar distributions. There's slight differences in the perimeter, but we notice that boiling is now gone, right? You're not going to see any boiling morphologies, but just frozen or flowing morphologies. Again, even in the Noachian, with 100 times higher pressure, it's still going to freeze every single morning. So these are only afternoon effects. So in conclusion, let's answer our initial questions. In the Noachian, we do find some Earth-like morphologies, and you also see a lot of freezing. In the Hesperian and Amazonian, you mostly find freezing, but some boiling can occur. Now, what about the prior work? Yes, we did confirm that those crazy results. So mud can levitate, and mud can look like Pahoehoe lava. This is going to be a very difficult task now for remote sensing. If these processes scale to the large features that we're looking at on Mars, it's going to be harder and harder to tell the differences unless we do some more work to quantify these differences in morphology between mud and lava. And we confirm this for all of our compositions, not just the mud that had been tested prior. Now, is this stuff true for the Noachian and Hesperian? So the answer is no. So the levitation is not going to occur during the Noachian. However, in the Hesperian, yes, you can have levitation and these lava-like morphologies. So finally, what do we do about these Earth analogs for these sediment flow features? And the answer is, you shouldn't really use them. They're not comparable unless you know that you're in the Noachian, unless you know that you're on a warm surface that's above about 30 millibar. And that's it. Thank you.
Hi, Eran Vos LMD. A very naive question, I think. What happens if it first boils and then freezes? What will we get in the end? What do we see if we look at it?
Yeah, so that happened during some of our experiments, where initially you get boiling, and that's along the first few seconds of contact and flow, because you have water that is infiltrating into the surface or coming out of the flow, and it starts to boil and explode. But ultimately, you might get freezing and a frozen crust. So this might have a combination of these morphologies that we're talking about. So it might be a little tricky to see, but you might be able to see both even in the same flow, depending on its size.
It as a different feature, maybe you can spot these ones because they are should be completely different than the rest of them. So maybe you have a transition between Noachian and Hesperian, or Hesperian to Amazonian, and then maybe you can spot different. I don't know.
Right. Yeah, that's a great point. And really what we want to do for the next step is look at these examples on Mars and try to understand if we scale up to Mars and can we see some of these morphologies? Where can you find the evidence? And can we use that to timestamp the paleopressure on Mars?
Hi, Jacob. Thank you. Really cool work. I like the ideas about using geomorphology to say something about the atmosphere as well. Quick question, because you mentioned scaling in your last answer, and I kind of wonder how certain processes like the Leidenfrost effect, but also things like surface tension, influence that sort of upscaling work that you would do.
That's a great question. So scaling is always going to be the issue. That's really the two things we can't do in the lab. We can't do kilometer-size flows, and we can't have Mars gravity. But the next talk by Caitlin is going to be about modeling. And with modeling, you can do both of those things. You could add gravity and you can scale up and investigate things like surface tension potentially, and if that would cause a big effect. So we don't know.
Okay, cool. I think the modeling is a good way to go about it. And we have recently done work in parabolic flights with at least mud flow, so we can discuss that later, hopefully, as well. And one quick question, more from an experimental side. Did you have any control on the partial pressure of water in the chamber? Probably no control. Did you have any measurements of the partial pressure?
We have a measurement of the pressure in the chamber, the total pressure in the chamber. And of course, as you're outgassing things as the mud comes out, it's going to change. So we didn't really define that as well, but we also can do other experiments, and there's some that are not in this paper that are purely about the boiling point. But we have not been able to investigate that in the lab.
I was just hoping maybe you had a cheap measurement device we could also use, but you don't.
Right.
I have to go searching for that.
Hi, Maxime Pinot, Université de Lyon. Very fascinating work, especially the pictures that you have shown us with the low base flow, with the levees. They are really looking like the temperate terrains, so that we have been looking earlier that week. Just a question, do you think that it's possible to do exactly the same experiments, but not using very fine particles, but mixing clays and sands probably, or silts?
Yeah.
What would you expect?
So we want to test all the compositions under the sun to at least know what some of the end members could be. It's cool when you see the final landforms and you just didn't know because no one's ever modeled it and we're not really sure what we're looking at on Mars. So I'd love to try more of that. We have all kinds of materials available. It's about time in the chamber, in the lab, but we should definitely test more of that.
Yes, thank you.
And on that note, our next plan is to create a mud volcano in the lab. So this has direct influence to your work, the thumbprint terrains, and we want to see how that looks in cold and warm and different environments. Thank you.
Again, thanks, Jacob, again. So the next speaker is Kathleen Frizzell, who will talk about modeling Martian mud flows.
Hi, thanks for being here. My name is Caitlin. I'll be talking about modeling Martian mud flows, the morphologic evolution and environmental sensitivity that we find using these models. As Jacob mentioned earlier, we did previously introduce the laboratory aspect of this, so I'm just going to be continuing. So, part of the reason we're all here today is because Mars climate history has a lot of unknowns. The pressure and the temperature, especially in the Noachian and the Hesperian, are not very well constrained. But we do have theories for, the warm versus wet, which is now even being called into question. And then like the punctuated events of surface water. These conditions control habitability and surface water stability on Mars's surface, so they're very important to try and constrain and understand. So paleoclimate, or the stability of surface water, is often inferred from like flow-like features, like Jacob mentioned, and the remote sensing, we can look at morphology, though this can actually lead to pretty ambiguous interpretations. We really find ourselves wondering, are these flow features truly caused by liquid water? Are they caused by salty water? Are they sediment flows? Under what pressure and temperature conditions did they occur? This has been quite a hot debate in Mars science for a long time now. You can see over here the phase diagram of water and kind of the range that you get in modern Mars versus Noachian with a bunch of question marks because we're not really sure how high the pressure got or how high the temperature got. So Earth versus Mars morphologies, you can see an image of Earth, an Earth terrestrial mudflow here, an example that was shown in the previous talk, as well as two putative Mars mudflow morphologies that were also shown in the previous talk. The flow features do appear to be similar between Earth and Mars. We see channels, lobes, deltas. It can be pretty tempting to maybe treat these as like paleoclimate indicators. But one of the major problems that was identified, especially with the laboratory work, is that we haven't really characterized how pressure, temperature, and salinity affect flow morphology shapes and just how these flows form and how they cool. So here on the right is just a summary image from the last talk. You can see that as you increase pressure, you actually see an increase in the extent of flow runout. So part of what I'm trying to figure out with my work here is, could the flows act as timestamps for past pressure? AKA, can we use the flow morphology as a proxy paleobarometer? So it would be really powerful for climate model calibration. And it would be really cool, but as we know, the processes that shape flows under the differing pressures and temperatures are really just not well characterized. So in the kind of like trifecta of remote sensing, modeling, and lab experiments, where does modeling fit in? Modeling can be used really as a way to branch the gaps that are identified between remote sensing and laboratory work. So laboratory experience and remote sensing give us tons and tons of data, which are phenomenal. Modeling can be used to bridge these gaps and understand the questions that come up during modeling and during remote sensing science investigations. So, So the project goals for this project were to predict end member morphologies across Mars-like parameter space. So looking at different dominant processes under varying pressure, temperature conditions, times of day, latitude, and potentially even obliquities. So we use a software called ComSol Multiphysics. We use this because it's flexible and versatile and allows us to incorporate a bunch of different physical parameters like cooling, boundary conditions, viscosity laws. And it's quite flexible in that the model allows you to turn on and turn off multiple different parameters so that you can fine tune and test the sensitivity of these parameters. So an overview, you probably saw this upper image in the last talk. This is the lab chamber setup. And then down below, we have a modeling setup. So basically, I modeled a mud flow on Mars on a 10-degree inclined slope, and we modeled just a 2D side profile. We used physics modules like laminar flow, heat transfer, non-isothermal flow, and then we defined the mud blob as a moving mesh that evolves over time based on the updating time step conditions. We did compare things like gravity, pressure, and temperature between Mars and Earth conditions. And yeah, you can see here on the right the image. So some of the model physics, the main driver of flow right now in the model is a temperature-dependent viscosity based on an Arrhenius law. We do also include temperature. So we have radiative heat flux at the mud-atmosphere boundary. We have kind of a weak convective heat flux at the mud-atmosphere boundary. And then we have a conductive heat flux at the mud base boundary. We model the basal temperature so that we can vary it beyond the laboratory constraints. And then we also include the radiative, convective, and conductive cooling so that we can kind of understand which cooling process is more dominant. So here are some of the results so far. What you're looking at here on the right is different Martian mud flows. And they're very simple morphologically, but you can kind of see that as you increase the temperature over time, your flow runout increases. And when you're watching the GIF right here, if you see a little thin green line, that is where the mud is quote unquote freezing based on its like temperature. So you can see that the mud freezes and then finishes its flow. But as you go down, and these GIFs run over a total of about 90 seconds, you can see that as you would expect, the warmer the atmospheric temperature, the longer your flow runout is. So we do see a flow length, that the flow length and thickness are strongly linked to the initial temperature, and that the cooling rate does control the truncation of flow, which is to be expected. We tested a range of around 100 Kelvin to 300 Kelvin just to encapsulate everything possible. This is something that is actively being worked on, the pressure effects. So we test anywhere from like 5 to 1,000 millibars. You can see here in the difference between 6 millibars and 1,000 millibars that there is a very, very, very tiny difference in flow runout length. So, you know, there is something here, but we realize that this is not fully capturing what we see in the experiments, and part of the biggest reason that this is happening is because we are not including an evaporative cooling approximation at this moment. So as soon as we start incorporating evaporative cooling, it should exaggerate this difference much more strongly. So we hope to continue working on this in the future. So model limitations, you can see here from the last talk some of the examples of like hovering, boiling, all sorts of things. This model is very, very first principles, very rudimentary. We are missing things like crust formation, levitation, laboratory phenomena, phase change, mass loss, and crystallization, and evaporative cooling. And these are all things that we are working on incorporating slowly into the model over time. And the model is flexible and does allow for you to add things after you establish the current physics. So we're hoping to get that going. So essentially, in conclusion, the modeling really does act as kind of like a missing link between laboratory and remote sensing, but I will say this as someone who does modeling and remote sensing, modeling would be nowhere without data points, so thank you to everyone who gets actual data points, because we can't really model anything without having that sort of constraint to rely off of. So our preliminary results so far do show visible trends in flow extent versus pressure, temperature, and gravity, which I don't have here in the presentation. They can potentially help us guide lab experiments and interpretation of remote sensing flows and features that we see on Mars's surface. Some of the final takeaways. One of the really important things I'm trying to establish here is that we really need rheological modeling in order to interpret climate from flow morphology. So laboratory experiments are cool, but we really need to understand what's going on there. The tool we're using, ComSol, is very flexible, it's great. Next steps, we do need to add evaporative cooling, crust formation, crystallization, phase change, et cetera. And then we can also scale up the lab results so that, as was mentioned earlier, we can see how surface tension and how other different physical processes vary over different scales. The bigger goal, essentially, is to connect climate models with observable features on Mars. So an example like model result up here would be if you were able to compare a flow B versus flow A on the right in remote sensing data to laboratory or modeling experiments. So you can see here that under one condition, under like 5 millibars pressure, you would have a shorter flow runout, and in your orbital image, your runout is shorter. And then on the bottom one, if you have higher pressures, you'd have a longer flow runout. So maybe some conclusions you could draw from this would be that flow B formed under higher atmospheric pressures than flow A. And this could be potentially powerful given crater age dating and understanding of the age of the surface. So it could help us kind of understand what the pressures were at what different points in time on Mars. But obviously, this is still a very, very large work in progress, but I will leave this slide with you, and that is my project. Thank you.
Do we have questions?
Thank you for this. It's really great work. I agree with you that we need models to step in between. You mentioned that you've not done the upscaling yet, so to Martian sort of not flow scales. Have you played around with gravity already?
I have, yes.
Ooh.
Yeah. So the model's really fun so far that we have been able to, obviously this is a Mars climate conference, so I didn't really talk about it here, but we are able to model also series conditions, for example, and it has been really interesting to see the effects of lowered gravity on the flow, to see the morphology that shows up from that, so yeah.
Could you give us a quick summary of what you think the gravity does, or at least what comes out of the models?
I do know the gravity does affect the flow runout and the flow shape. Usually, I think from what I've seen in the experiments so far is that the flow thickness specifically is controlled by the gravity, whereas if you have a higher gravity, your flow is thinner, and if you have a lower gravity, like something on Ceres or on the moon, your flow is very, very thick and kind of round.
Cool. And that then involves, I guess, also the rate of cooling of the flow, because if you get thicker, it's...
We have not yet tested the rate of cooling with the gravity measurements.
Okay, thank you.
Yeah.
Colin, JPL, thank you for this talk. And I have a question on the modeling and especially how you couple the interface between the atmosphere and the mud. So you said that you had convective and conductive boundary condition. Can you detail a little bit on that?
Yeah, so essentially we have the atmosphere implicitly defined in the model as opposed to explicitly defined. It's defined based on existing boundary parameters, and we are able to change things like the external pressure, the external temperature, and then we use equations of heat flux at that boundary that we are able to change based on the pressure and the temperature and different like activation energies.
Okay, and what about the coefficient? Generally, you have a coefficient which depends actually on the stability of atmosphere, stuff like that. Do you include it in it or not?
Yes, we are working with different heat flow coefficients. Right now, as I mentioned, it is still a very rudimentary model, so we're just using like very quick approximations, but these are things that I think are very worth exploring in the future because they can be dependent on different processes and they can very greatly affect the actual flow features.
Okay, thank you very much.
Yeah.
Hi, William Rapin, CNRS IRAP. Is the physics of your model flexible enough to adapt for other liquids other than water? Or?
Yeah, so we can adapt for other liquids. Something that I also think would be useful and potentially really interesting going forward is to model different flow concentrations or different flow mineralogies or even sediment concentrations. And then like liquid concentration, so like how close can we get to a total sediment flow while still getting actual flow motion? Like where do you need to add water in order for it to start flowing?
Second question is, you said next step is phase change, but we see the flow stalling though in your model already.
Yes.
So it's stalling because of the change of viscosity? There is no phase change?
Yes, yeah, so right now the flow truncation is approximated by a viscosity temperature relationship. We add basically like a tan H cutoff where once it reaches the quote unquote like freezing point of the mud, it increases in viscosity so much that the flow truncates. And we're doing that right now as just an approximation until we work in phase change.
Thank you.
Thank you. We can thanks our speaker again. So we are now moving to the present and past dust cycle and aerial transport station. First presentation by Thomas Pierron, who will talk about modeling present and past dust cycles with an offline model.
You can use the lighter like this if you want to. Yes, she was moving
Hi everyone, so my name is Thomas Pierron. I'm a PhD student at LMD, working with François Forget and Tanguy Bertrand. And today I will present to you my work on the modeling of the dust cycle on Mars. So the main processes responsible of the dust lifting on Mars are the surface wind stress, responsible of large-scale storm during the storm season, and dust devil that maintain dust in the atmosphere, mainly during the clear season. So this is 12 Martian years of observations of the dust opacity on Mars. So each figure here is a Martian year, and you have the latitude and the solar longitude in the axis. And this here I show the column integrated dust optical depth, and you see that there is a strong interannual variability. Some years you have extreme events, which are called global dust storms that occur some years and not others. And so you have a very strong interannual variability. But if you look at years without global dust storm and you average them, you see that there is always a certain pattern repeating each year with four main seasons, four main storms, the Z, the A, the B, and the C season. And between the two major seasons, the A and C, you have a pause which we call the solstitial pause. So if you want to model that with a numerical model, of course, you can use a GCM, but it's not the appropriate tool because a GCM is very slow. And when you model the dust cycle, you have sometimes to wait tens of years to reach a steady state. And also you want to model the dust cycle on a very long term, for hundreds or thousands of years. So we designed a new model, an offline model. The idea is that we run the GCM simulation at constant dust opacity from a very clear atmosphere to high optical depths, with an atmosphere with high dust opacity. And all these runs gives us a wind field, and we use this wind field to lift the dust and to transport the dust in our model. And then we can compute the planetary mean of the dust opacity in our model and use this planetary mean to interpolate the winds between the different GCM simulations. So this allows us to run very quickly hundreds of thousands of Martian years, simulate the dust cycle for the very long term, and still take into account the effect of the dust, the radiative effect of the dust on the winds. So here I present the different GCM simulation, the wind stress for the different GCM simulation, and basically what you see is that for a clear atmosphere, you have not so much strong winds, and the more dust you have in the atmosphere, the stronger the winds are. And so you can use this wind in the offline model. And if you use this wind in the offline model, you see that years after years, you will lose dust in the atmosphere because dust sedimentate in the model in region when the wind is not strong enough to lift it again. So you have a sink in the model. And so you need a source to compensate the sink. And so you can consider two possible dust sources, either erosion, so you allow the model to still leave dust in the atmosphere, even if you don't have dust anymore on the surface, but only at the condition that the winds are strong enough to erode the surface. And another possibility is to consider that there might be some region on Mars when you have huge amount of dust, and so you can consider this region as an infinite dust reservoir in the model. So these are the two possible ways to compensate the sink. Today I present the result for the erosion case, but both works. But today I will present the result for the erosion. So if you do that, you can compensate the sink and reach a steady state. And the steady states you reach is a maximum of dust opacity near the southern summer solstice, which is very different from the observation at the bottom, where you have the four main seasons that I showed before. And actually, all models have this maximum dust opacity at the southern summer solstice. And the reason why all models end up with this is that they do not really resolve the local processes that are responsible of the dust lifting on Mars. So resolution is too low. For example, if I show you here a GCM simulation at low resolution and on the bottom a high resolution run, you see that the wind magnitude is much stronger in the high resolution run, especially when you have baroclinic instability. Of course, the baroclinic wave is resolved in both models. It's a planetary wave. But the front of the wave is much thinner at high resolution. And so you have stronger pressure gradients, and so you have stronger winds. And in reality, the pressure gradients can be really strong. So here in the model, what we do is that we detect when we have a baroclinic activity, and we enhance the winds in the model when you have this strong baroclinic instability. And so this allows to create very realistic flushing storm on the model here on the left, thanks to this parametrization of the baroclinic wave. Another process that you don't capture well with low-resolution models is the fact that at the edge of the storm here, you can have strong dust opacity gradients and therefore strong temperature gradients, leading to high wind speed, able to lift the dust. And so we take that into account in our model by adding a wind at the edge of the storms, and here you can see the effect on the opacity of the model here on the storms. And so if you take into account all this, you can go from this maximum dust opacity at southern summer solstice to two main seasons, two main storms, the A and the C season, exactly like the observation here. Another process that is not well resolved by the low resolution is the fact that at the edge of the polar cap this time, you can have strong surface temperature gradients because the CO2 ice is very cold and the terrain just right next to it, it's much warmer. And the gradients, they are not well resolved by the models. Here you have the surface temperature of the models on the right, and here you need to enhance the winds because of the real surface temperature gradient that exists. And so by taking this into account, you are able to create local storm here near the cap edge at the solstice, exactly at the B season here, creating these storms exactly like it is observed in the observation. Also, another process is the fact that when you have a large-scale slope and it's partially covered by ice, there are mesoscale effects that enhance the wind and allow the lifting of the winds. And by taking this into account also in the model, you are able to reproduce kind of a Z season. So now you have the four main seasons that we observed in the observations. And of course, the last thing that you don't resolve in a model are these small dust devils here that are very local scale. They are only resolved by this kind of simulation, large eddy simulation, but they are not resolved by the global model. So you need to parameterize this by make the parameterization based on these higher resolution large eddy simulation. And you end up, by taking all this into account in the offline model, you end up with a dust cycle which is very close to the observation with the four main seasons that you have in the model and you have in the observation here. So a very good agreement for the seasonal cycle. But you also want to model the interannual variability and the occurrence of global dust storms. So this is the observation of two global dust storms, Martian year 25 and Martian year 28. One is occurring at the spring equinox and one at the southern summer solstice. And if you look at the global dust storm that occurred since 1956, you see that basically they either occurred around the solstice or either around the equinox. And so you have a variability in the season at which occur the global dust storms. And to introduce this interannual variability in the model, what we did is that we did parameterization of subgrid surface dust reservoir. So let me explain. The idea is that inside the grid cell, you have some place where the dust is really hard to lift, some place where the dust is really easy to lift, and so you can divide your grid cell in several subgrid dust reservoirs, and each reservoir has its own threshold to lift the dust. And so you can accumulate dust in high threshold reservoir for several years until it's lifted and create a global dust storm, and it takes several years again to replenish this high threshold reservoir. But you have still low threshold reservoir to always have dust available to create the regional storm. And so if you take that into account, indeed, for 100 Martian year simulation in the offline model, you can reproduce some years with global dust storm and some years without global dust storm. And what is interesting is that when this global dust storm occur in the season, some of these global dust storms occur around the equinox, and some of them occurs around the solstice, exactly like it is observed by orbiters. So here is the model for an equinoctial global dust storms, and here is the observation. So you see that the model, the global dust storm occur a bit lately in the season, but still it initiates in Hellas, like in the observation. And this is the model for solstitial global dust storm, and this is the observation, and the global dust storm occur a bit later in the season for the observation. And if you average all the year without global dust storm, you see that indeed for a 100-year simulation, all the year without global dust storm, they do have these four main storms, Z, A, B, and C, like the observations. Now, if you look at the dust at the surface after a 100-year simulation, you see that indeed the repartition of the surface dust at the end of the simulation has a good agreement with the albedo observed on Mars. Now the question is, what happened at high obliquity? So of course you can run the reference GCM simulation at high obliquity and use the same model to see what the dust cycle is at high obliquity. And so you could think, okay, I have stronger wind at high obliquity, so I will have, since today I'm right at the equilibrium between between global dust storm every year and no global dust storm at all, then if I have stronger winds, I will have global dust storms every year. But since we have limited dust reservoir, the model might adjust itself to years with global dust storm and years without global dust storm. But we have to take into account also the fact that we have a source in the model, an erosion source. So you might also have more erosion at high obliquity, and so might also create global dust storms every year. So this is the key question. Will the dust cycle self-regulate as today, or will shift to continuous global dust storms activity at high obliquity? I don't have the answer yet. I will have to test with my model. But meanwhile, I'm happy to answer to your question. Thank you very much.
Hi, Bruce Tchaikovsky, Colorado. Really exciting results on global dust storms at the present. One of the figures you showed looked at all the dust storms since the 1956 dust storm. And that brings up the issue that before 1956, the dust cycle appears to have been very different from what we see today. No global dust storms, and a factor of several smaller background dust opacity. Is there anything in your model that would give rise to that decades to century variability?
The fact that we don't observe global dust storms before 1956, it could also be that with telescopic observation, it's hard to say if we didn't miss global dust storm or not. But that's true that sometimes the variability is about you have to wait 3 years before having a global dust storm. Sometimes you have to wait decades before having global dust storms. And the model do have some variability in the frequency at which the global dust storm occur. But we cannot say right now what we are able to predict or to have the same pattern of exact same frequency that is observed as global dust storms, but we still have now a model that is able to have a certain interannual variability and with some difference in the seasonal occurrence of these global dust storms. But yeah, it's difficult to have something to compare before this date because we lack observations to really say to really have an idea of what is the real frequency of global dust storm. Is there a pattern repeating every decade or something like this? So I think we don't have enough years to know exactly the frequency.
I think that's right, but there are some good indications. The work that Zurich and Martin did reminded us that when the 1956 dust storm occurred, all those old-time telescopic observers were totally floored, never having seen anything like it, despite 50, 60, 70 years of observations. So I think there's a pretty strong indication of variability in the system.
Yeah. Great talk, thank you very much. I have a question on the albedo map that you showed. So you compare your model with the albedo map, and I'm aware of some papers like Bast et al. 2022 tracking the variability of the albedo of the surface for year before and after the storm. And I'm wondering if you have this comparison or it's a plan actually to compare and see the evolution.
I have made the comparison between the difference of the surface dust at the end of the global dust storms in the model and before the global dust storms to this map that showed the difference between the difference of albedo. But it is true that in these maps, what you see, the difference of albedo sometimes not just right after the global dust storm and before. And so you have sometimes differences about 1 year. And even if there is a global dust storm occurring during this year, the albedo changes can be misleading because sometimes you have dust outside the global dust storms that can have been lifted here and then sedimented here after, and so it's really hard to say from a albedo difference maps exactly where the dust has been lifted, because maybe a part of the dust that has been lifted where you have a lower albedo, indeed there are some lifting here, but there are also some sedimentation here, and so we would need difference with a much shorter time scale, I guess, like even for the increasing phase of the global dust storm, for example, the difference between the maximum dust opacity in the global dust storm and the beginning, and not differences of the scale of 1 year. So I've made some comparison. It's not perfectly in agreement, but we do see that indeed during the global dust storm there is strong lifting here, and we do see that the albedo changes here. Also in this albedo map, but that is true that, for example, here in Syrtis Major, after global dust storms, you see that the albedo is lighter here, but you have stronger lifting in the model. But that might be because you have strong lifting, but then after that you have also strong sedimentation. So this hides the reality a little bit.
And the second question I have is, do you plan to do some tagging as Tanguy has made, for instance?
With this model, I don't have done tagging, but it's something that we could do, and that would be interesting to do in the future, yes.
Last quick question.
Hi, Aurélien Chabinin, IRAP. Thank you very much for talk. Very impressive to see how well you about to reproduce the cycle.
Thank you.
I have actually it's a two-part question. First one is, you show that you have sometimes some discrepancies between the timing. Some storms occurs a bit like earlier, and even if you show that the average year, you can see that you have a small difference in timing. What do you think maybe see some ways to explore how we can reconcile and where it may come from? And then my second question is also regarding this albedo map you showed the distributions. Over which kind of timescale is the dust redistributed across the planet, or is there some region where the dust stays located and they don't really mix? I mean, yeah. What about the dust distributions?
Okay, so about the seasonal, at which season the global dust storms occur. It's true that in my model, they always, especially the one occurring around LS200 here, they kind of occur the same way every time they occur. And also they occur a bit lately in the season, like you have more global dust storms occurring here in reality, and in my model I just have one. But the thing is, this is a bit triggered also by baroclinic waves, baroclinic activity, and we know that the model doesn't have the perfect seasonal occurrence at which the baroclinic activity occur, especially when you base your model on constant dust opacity simulation. It has a good, it gives you a realistic wind field, but it's not perfectly representing the reality that occurs with where you have strong dust opacity gradients at large scale in the model, that you don't compute the real baroclinic waves that really occurred. So this could create a shift in the occurrence in the global dust storms. If, for example, you used all these parametrization that I use in a real GCM, because this is offline. And for the albedo changes, I didn't get very well your question.
Just a question about so the dust. I mean, so it's transported and redistributed. Over like which kind of time scale is the dust distributed across the planet, or is there some regions where the dust stays at the same place and it's not mixed with?
Yeah, of course. After few tens of years, you can say in the model where the dust is going to accumulate here, and you could extrapolate this for thousands of years, and that would be even interesting for obliquity variation. Like, for example, you can run this model at another obliquity, see after 100 years where the dust has accumulated and extrapolate this for several thousands of years and say, okay, here, this will create an infinite dust reservoir. And you can say that after, tens of years, because the equilibrium of, there are some reservoirs indeed that are going to accumulate dust and create infinite dust reservoir, and some other reservoirs that are adjusting and just creating global dust storms and then replenish again, and etc.
Thank you, Thomas.
Thank you.
We are moving on to the next speaker, who is Quentin Béton, who will talk about different factors that influence dust devils.
You can use this to... Great. Hi, my name is Quentin Béton. I'm a master student currently in North University, but doing my second master year in Freie Universität in Berlin. I will be presenting to you today the work I did under the supervision of Susan Conway this past year, which is about dust devils on Mars, and more especially the formation conditions of dust devils on Mars. So, dust devils, as they were presented by Thomas just before, are vortices that exist either on Mars or on Earth. On Earth, they are generally a couple 100 meters tall, but on Mars they can get up to several kilometers height. These are very short-lived processes, and being able to lift dust, they are then visible on images that we take with satellites. Depending on who you ask, dust devils can account to more or less of the total suspended dust on Mars. Some of them will say that they can account for up to 30 to 50% of it. Indirectly, with the dust lifting, they have an impact in the water-ice cycle, also with the atmospheric heating, and by removing dust from the surface, they also will very locally change the albedo of the terrain, either making it higher or lower, depending on the terrain below it. And for us, dust devils have quite a lot of benefits, which is that they are basically vacuums for us. So as you can see here, for our rovers or landers, they remove dust from their solar panels, increasing their lifespan by increasing their power intake. So during the work, I tried to answer a question, which is we have a lot of uncertainties about dust devils currently, mainly around their formation on Mars, the conditions of formation, whether there are the conditions of formation of dust devils looking at the atmosphere, but also where often dust devils form, what are the terrain factors that will mainly change the dust devil formation rates. This year, earlier in April, a paper was published by Conway and contributors looking at the CTX Mars Reconnaissance Orbiter data, which is of a 6 meter per pixel resolution. They used a machine learning model which looked at around 8 Martian years of records, and which translates into 132,000 images. And they did a first global panel of the dust devils occurrences that were taken in picture by this satellite. After this, I was able to use these datasets, and with also lots of contributors before me, in order to extract multiple parameters from it. Here is a capture of what we used, which is a platform called Zooniverse. This is a collaborative platform often used for citizen science, but here we used at a collaborative platform for our team. On each image that was taken, it was first validated if whether the devil was well detected or not. Then we extracted multiple parameters such as the brightest spot position and the reference terrain and a reference terrain area, which make us able then to extract a relative brightness of the dust devil. We also extracted the dust devil, dust devil shadow position and length to compute then its height. And with that, we also used data from the digital elevation model of MOLA with a resolution of about 200 meters per pixel, and also thermal inertia and albedo from the test data with a resolution of 3 kilometers per pixels. Additionally to this terrain data, we also wanted to look more into the atmospheric particularities of this device formation. And since these are very short-lived processes, we needed to use a meteorological model rather than a climate one. So we used OpenMars, which is a model that was published and created by James Holmes and contributors in 2020 with recent updates. This model have a record of around 9 Martian years of modelization. This is a global circulation model assimilating orbiters data and extrapolating. And we extracted lots of parameters, but mainly 3 of them: the absolute wind speeds of when and where those devices were captured, the temperature difference between the air and the surface at this location, as well as the planetary boundary layer height at the time of the those device formation. This made us able to look at the distribution of the Zivil formation. Here you can see a plot showing the background wind speeds relative to the surface air temperature difference. This is a density plot of the Zivil population, and we can see that the formation condition the most represented are a temperature difference of about 23 Kelvin and wind speeds, background wind speed of around 8 meters per second. This is very well-bounded data, over 20 meters per second or even a bit above 45 Kelvin. We do not see any dust devil forming or very much less dust devils. We also wanted to look at hypotheses that were detailed by researchers in the past. So we looked at 2 hotspots that are known on Mars for dust devils, which are Amazonis planitia and Arcadia planitia, you can see on the map here. There was a survey done now 10 years ago by Fenton and Lawrence, which looked at the influence of the planetary boundary layer height regarding to the dust devil height itself. In their data, they showed that the mean dust devil height showed the same evolution as the planetary boundary layer height, increasing when the planetary boundary layer height was increasing and decreasing with it also. We did the same analysis where all data set at the same location, and we had quite different results. So this is a plot showing the entire dust devil population regarding, not regarding out the years. The mean dust devil's height aren't really great on this plot, but you can see them here increasing constantly, pretty much constantly, until 180 degrees of solar longitude, which is not the same trend. We do not see a decrease before just not seeing dust devils anymore. And we redid the same analysis on Arcadia planitia, where we can see exactly the same trend with an augmentation of dust devil height up until 180, 190 degrees of solar longitude, and then an absence of dust devils After that, we also wanted to look at different terrain factors. And when we first looked at, I'm going to go back to the map from Conway et al. When we looked at the spatial distribution of dust devils regarding, for example, the dust cover index, and after that, the thermal inertia, we saw that they were bounded near great surface contrasts or gradients of the thermal inertia, and we wanted to look more into the exact distances to these gradients. And what we saw was that dust devils were well bounded once again, with still quite high distances from this contrast, but pretty much all of them were near about 250,000 meters from this contrast. With this relation being much better shown in dust devils presence at much higher latitudes than -40 degrees, but still clearly seen in the southern hemisphere data. Here you have the entire data set. From this work, we were able to extract some major information for the devils formation, which are the temperature difference of 23 Kelvin and the wind speed of 8 meters per second. The hypothesis of Fenton and Lawrence is not shown in our data, at least it doesn't support it from what we know. And it has major implication in future work and past work on those devils. Notably that since now we have for the first time information on dust devils formation on a global scale on Mars, this can give scopes to improve GCMs and better estimate the role of dust devils in the total volume of suspended dust, which is still a big question currently on modeling Mars's climate. We also have to investigate further why the planetary boundary layer height do not modulate that much the dust devil height itself. And since now we are currently having more information about the surface factors influencing dust devils formation, we could also find new regions of interest that we could monitor better in the future in order to have more data and have kind of a feedback loop, a good feedback loop, to have better data on dust devils and learn more about these processes. Thank you, and thanks to all my contributors.
Any questions in the room?
Hey, I'm Michael Mishna, JPL, and thank you very much for that presentation. Just one question: the Open Mars database has I think it has a underlying resolution of like 5 by 5 degrees, which is a pretty big swath. And I'm just wondering if the output of that model for things like wind speeds in a grid box might potentially be smoothing out some subgrid scale heterogeneities that might tweak those numbers you showed in the last slide there. If you've given some thought to studying something at higher resolution, maybe another database like eMars or something like that. But.
Yeah, it definitely smoothed out these values. The most interesting thing about this model was the temporal resolution of it, which we can have up to 12 minutes resolution for the time step. Yeah, we haven't really. I don't have any idea of how much this will impact the results because I haven't looked at more high spatial resolution, but this is still a trend we see throughout now 14,000 dust devils. So I would be very happy to discuss more in depth about it with you after that. Yeah.
Sure. Yeah, actually, as I'm thinking about it, dust devils tend not to form in areas of steep and transitional topography. So maybe it kind of comes out in the wash because winds are going to be pretty uniform over the types of surfaces that dust devils tend to accumulate in. So as I think about it, maybe it's not an issue at all.
Well, yeah, we looked at slope for the dust devil formation, and definitely I can show you the plot after this, but we see that pretty much all of the dust devils will form on slope lower than 1 degree. We have dust devils forming at much higher slope. We have a lot of research done on dust devil tracks that are going upward slopes, because it has been detailed that it can help dust devils move and upward these slopes. But yeah, most of our data sets is forming on less than 1 degree slope.
Thank you.
Thank you.
Thank you, Quentin. I think we are moving on.
Great. Thank you.
Thanks, Quentin, again. And we are welcoming for the last talk of this morning, Sitang Fan, on the behalf of his collaborator. We will talk about global surface wind patterns through transverse aeolian ridges.
Not working? Okay, I just use the mouse here. Okay, it looks like we are a bit behind the schedule, so I'm sorry for standing between you and the lunch. The second, since I assume you are as exhausted as I am on the Friday morning of the Dance and Wonderful week, especially after the dinner cruise last night, so I put my take-home message in the front. So in this work, we did a global mapping of the transverse aeolian ridges and inferred a surface map of the near recent. We have the map of the near recent winds. So third, I will present how we did it. I'm Sitang Fan here from the Southern University of Science and Technology, or you can call an acronym SUSTEC. This work is mainly carried on by my colleague Yiran Wang, the second one here, and her PhD student, Zhaoran Wei. This is a work I'm collaborating with, and I find it more relevant to this conference than my own research on the present-day atmosphere. So in this work, we are trying to find some surface evidence of the wind in the recent past. The surface feature we focus on is the transverse aeolian ridges. They are wave-like ridges formed through the saltation of sand grains and deposition of the finer particles. They show high albedo in the images and a symmetric cross-section. They are thought to be formed on the bed forms with a size of tens of meters and with non-uniformly distributed grain sizes. Since they are features, they are from perpendicular. They are thought to be from perpendicular to the prevailing winds and show limited present-day activities. So they are good proxies of the near recent wind because they can freeze the wind pattern on the surface. So the data we use in this work is the MRO CTX, the global Mosaic version 1 release. It contains data from 2006 till 2020, consisting of 90,000 images covering almost the entire globe of Mars, from 88 degrees south to 88 degrees north, with a resolution of 5 meters, and total number is around 4,000 tiles. We analyze in this work. Since detecting the feature is a typical problem for the image recognition, so we use the machine learning technique, SegFormer, which is developed based on the transformer to do the image recognition. We feed the model with thousands of manually labeled features, and then train the model, and the model returns the result. Here I'm showing the performance of the model. The first one is the precision, which is the true positive over the true plus false positive, which means that among the features we find, how many of them are correct by a fraction. The second one is the recall rate, which is the true positive over the true positive plus false negative, which means that among all the correct results, how many did we find by fraction? So, which means that we, using this model, we detected around 80% of the features, and among the features we detected, 98 of them are correct. So this is kind of a good performance of this model. So here's the map we derived using the result. We detect more than around 90 million features around the globe, and of the TARs, they mostly distributed from low to mid latitude, co-aligned with the region we think the water activity took place. And also we did the similar stuff for the wind strikes. So it totals about 22,000 in number. use it as a for a reference or the comparison, since wind strikes can infer the kind of the current wind pattern in this work. So the next step is that so how do we determine the direction of the transverse aeolian feature ridges? So we use a two-dimensional Fourier transform. It's a French name. So the two-dimensional Fourier transform in this. Is that correct? Yeah. Okay. Good. So the rationale using this transform is that if we go along the wind direction, it forms the transverse aeolian ridges, and so that introduces the fluctuation in the topography. That means that we put high energy into the topography. So if we do the transform, we'll see a bright spectrum along the direction frozen by the surface feature. So we can determine the wind direction using the result from the transform. So here comes the result. Here's a kind of a global map from low to mid latitude, at least from low to mid latitude, and the colors denote the direction determined by the transform. We find good consistency, regional consistency in all these regions. So if we connect the directions, we have these black lines. They are kind of streamlines for the wind pattern. And since the ridges are on the order of a few tens of meters, so we can also derive the wind pattern from global to regional to local scales. So if we zoom in this image, we can find some small structure, even smaller, like this ones along the ridge of the kind of a crater ring. So the next step, we would like to compare the global wind pattern with the model, and so we zoom out and to use the model resolution as shown here. These lines are the ones inferred from the TARs, and we did the same thing for wind strikes using the downwind feature of the craters. So they show very kind of good consistency, and so this is a map we derived from the TARs. So the next step, we did a comparison with the GCM output. Here I'm showing you the results. The top one is the one for we run for with the orbital parameters at 1 million years ago. So we used all the eccentricity, obliquity, and perihelion shown in the EPIC LASCAR 2004 paper, and the lower right is the one for present day. The setting of this GCM is that we used a constant uniformly distributed dust profile following Conrad's profile with a column normalized column optical depth of 0.2, and then the results shown here are for the winter, because we basically the major reason is that we find is the agreement is the best during winter. Since winter is the time with the strongest wind, so that's another indication of the nonlinear response of the surface feature to the wind. The agreement for the winter pattern is better than that if we use the annual mean. So Richardson and Wilson 2002, and also from these images, from these pictures, we can also see the surface pattern seems not to change in the past few million years, no matter how the optical parameters changes. It is also suggested by Fenton and Richardson 2001, since this is mostly regulated by the topography and the boundary layer. And from here, we run the obliquity as 35 degrees because it crashes at 40 degrees. And I think that's typical problem for the model to run high obliquity. And from here, the conclusion here is that we see the best agreement during winter and during 1 million years ago. So this one. And if we zoom in to some regional scale, we find probably here in the convergence region of the wind, we see the TAR inferred pattern is agree with the model better. So next question is that what is the age of the wind field seen on the surface? So we did a standard crater counting for inferring the age of the transverse aeolian ridges. So we select the regions with these features, and we count the craters on top of the features, and then we have this fitting of the function of the impact flux. So we derive the age of this feature. So here comes the result. During the crater counting, we find most of the ridges are formed within at 4 plus minus 1 million years ago. It coincides with the time when Mars transited from the high obliquity to low obliquity. And from the surface images, this one is taken by Zhurong rover. We see some water activities included in we find it should be in the consolidation of this feature. So we think we are deriving a surface feature that formed during the time, or we derive an evidence of the redistribution of the surface water in the recent time. So to sum up, we derived a high-resolution global map of the recent near-surface winds using the deep learning techniques and then the transform as well as the crater counting. So if you, since I'm an atmosphere person, if you have very detailed question about how to set up the model or how to do the counting or how to do the transform, here's the email of my colleague. Anything else? Here's the email of me. I will try to handle the questions. Thank you.
Hey, Sidang, really nice work, Eran Vos, LMD. You showed that you chose to show present day and 1 million years ago, and with a constant dust obliquity of 0.2. But I was wondering that the wind is a factor of so many different parameters. How can you decide which one is the dominant ones that create the TARs, and how do you explore this huge parameter space?
From the result, we find that the wind patterns look like the same. So they do not change a lot, no matter how you change the parameters. And here I'm showing the pattern in winter, and it's always strong in winter. If you, for the present in Mars, if you flip the solar longitude of the perihelion and the aphelion, the wind field look like almost the same. So it does not matter that much.
Really, I'm really surprised that if you change the dust opacity, you still get the same wind patterns, because this wind is driven by a difference in pressure, and if you have if you have higher dust opacity, the pressure should the difference in pressure should be more constant.
Yeah, I think the thickness or the surface pressure would have an influence. For this thin atmosphere setting, we do not see that much change.
Thank you so much.
Thank you.
Hi, this question is coming from maybe a position of naivete, but what is preventing TARs from being formed today? Why? I mean, a million years ago, essentially the same environmental conditions, I would think. So why are they not? Or maybe they are being formed today. I don't actually know.
First, I'm not a geology person. To my understanding, is that we probably need some of the water to be there, or sufficient amount of water, ice there to consolidate this stuff.
Don't look at me. I'm not a geologist either, but I don't know that there would be much more water a million years ago. Bryony.
Yeah, well, Bryony Horgan, I was going to ask, along those lines, actually, I was going to ask, because, we have a really nice in situ study from the Opportunity rover in Meridiani. They were able to do crater counting on TARS they were driving through. I think that was like 40,000 years was the age on those. So they're much more recent. So I was just curious if you all have thought about comparing your map and results to like some of the ground truth that we have from the rovers, for example.
Not yet. We just do the global stuff, and we find we did the Tierra and the wind strikes. They show some good consistency from at this scale. Since we have some local scale results, we can definitely do that. Thank you.
I first wanted to say this quite very, very impressive. I've never seen such a study. And second, just a suggestion for when comparing with the models, maybe you could do a little more based on actually some people on the Earth have done stuff like that, but using processing the data by looking at the maximum wing, maybe with an index with the high resolution, not without average, so that you could take into account barocutating wave front and also not just looking at winter. You could improve that and throughout the year, and I'm sure you can do that very well. Maybe the agreement will be worse or better, but it will be different.
Well, actually, it's worse. We tried that. we tried that. We tried the maximum wind and use that direction, but we still find that the mean field during winter shows the best agreement. So that's the reason why I'm showing this picture. So we compare the annual mean, the seasonal mean, and also the maximum versus average, and we find the seasonal mean during winter is the best, and 1 million years ago, this is the best one. The 1 hour, I think the output 1 hour, 1 hour output.
Jim Head, Brown University. This is a really excellent, informative study. I would really encourage you to compare the results in Southern Utopia, Planitia, with the Zhurong rover, your Chinese Zhurong rover mission, because in fact we've noticed, I've worked with some of my colleagues there, we can look at the geological record during this time period because it's exploring the edge of the latitude-dependent mantle, and we see stratigraphy that is actually related to this process. So there's a paper by Chunlai Li et al., et cetera. Really
I know that one. You also see some change of the wind direction from the ridges. We try to solve that problem, but right now we find the model that the wind field does not change. So we are still trying to figure that out.
Well, there's also some temporal information there too that we tried to correlate. So I mean, in terms of the sequence of events and the actual ages associated with the global pattern. So I'm happy to talk to you about that. It's great.
Yeah, sure. Yeah, thank you.
So we can thank our speaker again, all the speakers. And we are reconvening at 2 p.m.